Hello, friends. Welcome back. Or if this is the first time you've found your way here, welcome. I'm so glad the night brought you here. Close your eyes for just a moment. Imagine standing in an open field, far from any city, far from any noise. The sky above you is impossibly deep. And then you look up and you see it. Not one sun, but two. Twin lights hovering low on the horizon, painting the sky in shades of amber and violet at the same time. One star, warm gold. The other, a pale icy blue. Two suns setting together, slowly, silently. Like they've been doing this for billions of years, and they're in no rush to stop. Here's what will quietly rearrange something in your mind tonight: that sky isn't science fiction. More than half the stars you see above you right now as you listen, belong to systems just like that. Two stars bound together, turning around each other in a dance that has never once stopped. We live around a single star, and we've come to think that's normal, but out there in the quiet dark, being alone might actually be the exception. Before we drift into that darkness together, if these slow, wonder-filled journeys bring you a little comfort, a little peace, at the end of a long day, you might like to stay a while. You can gently press the like button. It costs nothing, and it means everything. Subscribe if you'd like more nights like this one, and ring the little bell softly, not for noise, but so the next quiet story can find its way back to you. Now, let's drift. Tonight we begin at the beginning. Not with equations, not with telescopes, but with a feeling. The feeling of looking up and realizing the universe is far more companionable than we ever imagined. For most of human history, the night sky was a ceiling of mystery. Ancient Babylonian astronomers cataloged the stars around 1200 BCE, mapping their positions with remarkable precision onto clay tablets. The Egyptians aligned their temples to specific stars. The Greeks named the constellations after heroes and monsters, as if they needed the sky to be full of stories to make sense of it. And in all that time, all those thousands of years of watching, almost no one thought to ask a simple question. What if two stars that appear close together in the sky are not just neighbors by coincidence, but are actually connected? It seems obvious to us now. But for centuries, that question simply didn't get asked. And the reason is surprisingly human. When you look at two stars close together in the night sky, your instinct tells you they're near each other. But instinct, as we'll discover again and again tonight, has a complicated relationship with the cosmos. There is a star system in the constellation Perseus called Algol. You can find it with the naked eye on a clear night. The ancient Egyptians noticed it. The Arabs named it Al-Ghul, which means the demon or the ghoul. Because Algol does something unsettling. Every 2 days, 20 hours and 49 minutes, it dims. Not fades, gently dims, noticeably, dropping to about 1/3 of its usual brightness, then slowly recovering over the course of hours, like an eye blinking, like something alive. For thousands of years, people found this deeply uncomfortable. The star that winked. Cultures across the ancient world marked Algol as unlucky, malevolent, connected to evil. Medieval astrologers warned against making important decisions when the demon star was active. And yet no one, not the Babylonians, not the Greeks, not the medieval astronomers of Persia and Arabia who had access to sophisticated mathematics, no one correctly identified what was actually happening. The answer, when it finally came, was something almost more beautiful than the myth. Algol isn't one star, it's two, and we'll come back to exactly what makes it do that mysterious wink, because understanding Algol is one of the most quietly astonishing stories in all of astronomy. But first, let's settle into why binary stars exist at all. Because they aren't accidents, they aren't rare exceptions. They are, in a very real sense, the universe's preferred way of making stars. Stars are born from enormous clouds of gas and dust structures so vast that our entire solar system would fit inside one of their smallest eddies. Scientists call them nebulae, and they drift through galaxies like slow, cold weather systems, sometimes for millions of years. Then something disturbs them. a shockwave from a nearby supernova, the spiral arm of a galaxy sweeping through, even the gravitational nudge of another cloud passing close. That disturbance causes parts of the cloud to begin collapsing inward under their own gravity, slowly at first, then faster still, the way a whisper can gather into a roar. As the cloud collapses, it doesn't collapse evenly. It fragments. Like a vast sheet of ice cracking into pieces, the cloud breaks into multiple collapsing cores, each one destined to become its own star. And when two of those cores form close enough together, something extraordinary happens. They don't just become neighbors, they become gravitationally entangled, bound, partners. Research suggests that somewhere between 40 and 80% of all sun-like stars in our galaxy are part of binary or multiple star systems. Some estimates go higher. The exact number is still being refined as telescopes improve and survey methods become more sophisticated. But the core truth is consistent. Single stars like our Sun are statistically speaking somewhat unusual. The universe seems to prefer company. Think about what that means for a moment. When you look up at the night sky and see a star, a single point of light, there is a better than even chance that what you're seeing is actually two stars so close together and so far away that your eye cannot separate them. They appear as one. They move as one. But they are two. Bound together by gravity circling each other in the dark, each one a sun in its own right. There's something about that image that stays with you. Now, when we say binary star, it's worth pausing on what we actually mean, because the term covers an extraordinary range of relationships. Some binary stars orbit each other so closely that they actually touch, sharing their outer layers of gas, like two flames merging at their edges. Scientists call these contact binaries, and they look less like two separate stars and more like a single peanut-shaped object tumbling through space. Other binary pairs are so far apart that one star would take millions of years to complete a single orbit around the other. Their gravitational bond, so gentle it barely registers, like two old friends who live on opposite sides of the world, but still belong somehow to each other. And then there's everything in between. Wide pairs, close pairs, pairs where both stars are nearly identical, the same mass, the same temperature, the same soft golden light. And pairs that couldn't be more different. One star a blazing blue giant, hot and young and burning through its fuel at a furious pace, and beside it a cool red dwarf, so dim and small it would barely be visible from a nearby planet. The variety is genuinely humbling. And it raises a question that astronomers have sat with for a long time. Does having a companion change what a star becomes? The answer, and this is one of those places where science becomes quietly profound, is yes. Deeply irreversibly yes. A star that forms alone lives a very different life than a star that forms beside another. The companion changes everything, the rate at which the star ages, the kind of death it will eventually die, the elements it scatters back into the cosmos when it's gone. We are in a very literal sense made of material that was forged and scattered by stars that died. And many of those stars may have died the way they did, precisely because they had a partner. We'll explore all of that slowly, gently as this night unfolds. But let's return for a moment to the simplest and most ancient version of the question, the one that a person standing in a field 10,000 years ago might have asked, staring up at a sky full of paired lights with no names and no framework, just wonder. Are those two stars up there together, or are they just close by accident? It took humanity an extraordinarily long time to answer that question. Not because the tools weren't eventually there, not because the math was too difficult, but because the idea itself that two stars could be gravitationally bound to each other, orbiting a common center, following the same laws that keep planets circling the sun, that idea required a kind of conceptual leap that is easy to underestimate. The leap required someone to believe that gravity, the force Newton had described in 1687, the force that held the moon in orbit around the Earth and the Earth in orbit around the sun, extended beyond our own solar system. That it was not a local law, a rule that applied only here in this familiar neighborhood of planets and one familiar yellow star, but a universal law, a law that reached across the incomprehensible distances between the stars. That someone was William Herschel, and the story of how he arrived at that understanding is one of the quieter revolutions in the history of science. Herschel was born in Hanover in 1738. He came to England as a young man, worked as a musician, an organist, a composer, a conductor, and taught himself astronomy the way some people teach themselves languages obsessively joyfully in every spare hour. He built his own telescopes, grinding his own mirrors by hand in a process so laborious and so precise that professional instrument makers of the era were baffled by how he achieved the quality he did. And he pointed those telescopes at the sky with a patience and thoroughness that was by any measure extraordinary. Beginning in 1779, Herschel began systematically cataloging what he called double stars, pairs of stars, that appeared close together in the sky. His original intention was purely geometric. If two stars appeared close together, but were actually at very different distances from Earth, then as the Earth moved around the Sun over the course of a year, the closer stars should appear to shift slightly against the background of the more distant one. By carefully measuring that shift, Herschel hoped to calculate stellar distances, a problem that had resisted solution for centuries. What he found instead changed everything. Over 25 years of observation, Herschel noticed something he hadn't expected. Some of his double stars weren't just close together in apparent terms, they were actually moving relative to each other. One star was orbiting the other. Slowly over years and decades, the angle between them was changing, not in the way you'd expect from a perspective shift as Earth moved, but in the way you'd expect from two objects gravitationally bound and circling a common center. In 1803, Herschel published his findings. He had confirmed the orbital motion of multiple double star systems, and in doing so, he had proved something that no one had ever proved before: gravity works the same way between the stars as it does within our solar system. The universe, at least in this fundamental respect, plays by the same rules everywhere. It seems straightforward now. Of course, gravity is universal. That's almost the definition of a law of physics. But in 1803, this was not obvious. This was not assumed. This was a discovery, a genuine world-rearranging discovery, made by a self-taught musician who built his own telescopes and spent his nights measuring the slow, silent movements of distant lights. There's a kind of beauty in that story that science doesn't always tell loudly enough, and here is something worth holding on to quietly as we move deeper into the night. The binary stars that Herschel was watching, those slowly orbiting pairs, had been circling each other for billions of years before he ever pointed a telescope at them. They didn't need him to notice them. They didn't need anyone to notice them. They just kept turning slowly in the dark, following a law they had no awareness of in a dance that had no audience for most of its history. Which raises a question worth sitting with. How many beautiful things are happening right now in this exact moment with no one watching? Have you ever looked up at the night sky and wondered how many of those stars are actually alone, and how many are quietly sharing the dark with someone else? The answer, it turns out, is written in the light, and learning to read that light is where the real story begins. And that story, the story of how astronomers learn to listen to starlight, to hear what it reveals about hidden companions, begins with something that looks at first glance like nothing more than a smear of color. That smear of color, that quiet ribbon of light, that starlight leaves behind when passed through a prism, turned out to be one of the most powerful tools humanity ever accidentally discovered. But before we get there, we need to sit with the misunderstanding first. Because the history of binary stars is not just a story of discovery. It is in equal measure a story of assumptions that held science back for centuries. Assumptions so reasonable, so logical, so perfectly sensible, that questioning them felt almost unnecessary. And that is where the most interesting errors always live. Let's go back to the sky. Not the sky as we understand it now, mapped, cataloged, measured to extraordinary precision. The sky as it appeared to someone standing in ancient Greece or medieval Persia, or Renaissance Europe. A vast dark dome studded with points of light that moved in predictable cyclical patterns, reliable, orderly, almost mechanical in their regularity. Within that orderly sky, there were anomalies, stars that seemed to travel in pairs, stars that sat side by side night after night, year after year, never drifting apart, never coming closer, just sitting there together, steady and unchanging. The ancient Greeks noticed them, Arab astronomers cataloged them, and the nearly universal interpretation across cultures and centuries was those two stars happen to be in the same direction. They are not together. They are simply lined up by coincidence from our point of view. This interpretation had a name. Astronomers would eventually call it an optical double two stars that appear paired but are actually at vastly different distances, with no physical connection whatsoever. And the assumption for most of human history was that this was the only explanation. Stars could not actually be orbiting each other. The distances between stars were surely too enormous for gravity to reach across. Our solar system had gravity. Between the stars, that was just empty, lawless space. It is worth pausing here to appreciate how reasonable that assumption was. Because we sometimes look back at historical misconceptions with a kind of comfortable superiority, as if the people who held them were simply not paying attention. But the assumption that stars couldn't orbit each other wasn't carelessness. It was logic. Clean, careful, well-reasoned logic. The distances between stars, even by rough ancient estimation, were incomprehensibly large. Why would gravity, a force that clearly operated at human scales, at solar system scales, stretch across that void? The answer required a conceptual shift that took centuries to arrive. And it arrived not with a dramatic announcement, but with something much quieter, years of patient, meticulous measurement, by a man who started out trying to solve a completely different problem. We met William Herschel briefly before his discovery in 1803 that confirmed stars truly do orbit each other. But the deeper history of how humanity arrived at even the tools to ask that question stretches back further and winds through a series of minds and moments that deserve to be known. One of those moments involves a star called Mizar. You can find it tonight if the sky is clear in the handle of the Big Dipper, the second star from the end. Mizar has a faint companion star, very close to it, visible to sharp eyes as a faint smudge, even without a telescope. The Arabs knew about this pair they called the companion Alcor, and used the ability to see it as an informal test of eyesight. Sharp vision, you can see Alcor. Poor vision, you cannot. Simple, practical, entirely focused on human vision rather than on what the stars themselves might be. In 1617, Benedetto Castelli, a student and close friend of Galileo, pointed a telescope at Mizar and noticed something. There wasn't just one companion. There were two stars very close together, where the naked eye had seen only one. He wrote to Galileo about it. Galileo noted it with interest. And then, like so many observations in the history of science, it was filed away without full understanding of what it might mean. Mizar, it turns out, is not just double. It is at least quadruple four stars gravitationally entangled moving together through space. It was the first double star ever observed through a telescope. And for nearly 200 years after Castelli's observation, it was treated primarily as a curiosity, a demonstration of telescopic power rather than evidence of a new kind of astronomical object. This is a pattern worth noticing. In the history of science, the instruments often arrive before the ideas needed to interpret what they show. We see something new, we note it, we file it, and then we wait sometimes for generations for someone to ask the right question about what we've been looking at. The right question in this case was Herschel's, and his path to asking it is itself a kind of lesson in how science actually moves, not in straight lines, not in sudden leaps, but in long winding arcs that often begin somewhere unexpected. Herschel's original project, remember, was parallax. He wanted to measure the distances to nearby stars by observing how they appeared to shift against more distant background stars as Earth moved through its orbit. The logic was sound. The geometry was elegant. The execution was extraordinarily difficult, and his chosen method comparing close pairs of stars, assuming the brighter one was, closer rested on an assumption that turned out to be frequently wrong. Some stars appear bright not because they are close, but because they are intrinsically luminous. A distant giant can outshine a nearby dwarf by a factor of thousands. Herschel's assumption that bright meant close was the same kind of clean logical error that had led astronomers astray about optical doubles for centuries. Reasonable, understandable, and in many cases, incorrect. What saved his project? What transformed a flawed parallax survey into one of the most important observational campaigns in the history of astronomy was precisely the flaw. Because in looking for parallax shifts in double star systems, Herschel was forced to measure those systems with extraordinary precision and patience over many years. And in doing so, he noticed what the parallax model couldn't explain. Some of these star pairs were moving relative to each other in ways that traced out orbital arcs, not the back and forth wobble of parallax. A smooth, continuous curve, the path of one body moving around another. By 1803, after more than 2 decades of observation, Herschel had enough data to make the case. Several double-star systems showed clear orbital motion. The stars were physically associated. They were bound by gravity, and gravity, therefore, was not a local phenomenon. It was universal, operating across the void between the stars, just as surely as it operated between the Earth and the Moon. The paper he published that year is, by the standards of transformative scientific documents, almost gentle in its tone. No dramatic proclamations, just careful tables of measurements, patient descriptions of what he had observed, and a quiet conclusion that rearranged the conceptual architecture of astronomy. The universe was not a collection of isolated stars standing at independent stations. It was a web of gravitational relationships, extending in every direction, at every scale. Here is a question worth sitting with. How many of the things we currently believe to be isolated, unconnected, independent, standing alone, are actually in quiet relationship with something we haven't yet thought to measure? Science has a long history of discovering that apparent isolation is often just the limit of our instruments. Now, even after Herschel's confirmation, the study of binary stars moved slowly for several decades. The reason was partly observational, measuring the slow orbital motion of stars that take hundreds or thousands of years. To complete a single orbit requires extraordinary patience. But it was also partly conceptual. Astronomers now accepted that binary stars existed, but they didn't yet appreciate how common they were, or how strange and varied the relationships between paired stars could become. The next great leap came from an entirely different direction, not from watching stars move across the sky, but from analyzing the light they emitted. And this is where we meet one of the most underappreciated tools in all of science, the spectroscope. The spectroscope, in its simplest form, does nothing more than split light into its component colors, a rainbow stretched out and magnified, revealing the specific wavelengths that a light source emits or absorbs. Every element absorbs and emits light at specific characteristic wavelengths, producing a unique pattern of dark lines, in a spectrum the way a fingerprint produces a unique pattern of ridges. Hydrogen produces its lines. Calcium produces its lines. Iron produces its lines. By reading those lines, an astronomer sitting on Earth can determine what a star is made of, even a star hundreds of light years away. This alone was remarkable enough. But in the 1880s and 1890s, astronomers began to notice something else in stellar spectra, something that shouldn't have been there, something that turned a fingerprinting tool into a detective's most powerful instrument. When a star is moving toward us, its light gets compressed, slightly shifted toward the blue end of the spectrum. When it's moving away, the light gets stretched, shifted toward the red. This is the Doppler effect, the same phenomenon that makes a passing siren seem to change pitch. And in stellar spectra, it showed up as a tiny but measurable shift in the positions of those characteristic dark lines. In 1889, an astronomer named Edward Pickering at the Harvard College Observatory was studying the spectrum of Mizar, yes, the same Mizar that Castelli had noted, with a telescope nearly 3 centuries earlier. And he noticed something extraordinary. The spectral lines of Mizar didn't just sit in one position, they split. Periodically, where there had been a single dark line, 2 lines appeared, one shifted slightly blue, one shifted slightly red. Then they merged back together, then split again. The interpretation was startling in its elegance. There were 2 stars in Mizar's light, too close together to separate visually. But one was moving toward Earth, while the other moved away, and then as they continued their orbit, the motion reversed. The split lines were the 2 stars announcing themselves each with its own Doppler signature, each carrying its velocity in the language of light. Pickering had discovered what we now call a spectroscopic binary, a double-star system that can only be detected through its spectrum because the stars themselves are too close to separate with a telescope. And in doing so, he opened a door that would reveal an entirely new population of binary stars, invisible to direct observation, but speaking clearly in light. What followed over the next few decades was a systematic re-examination of stellar spectra and a growing realization that many stars that appeared single were in fact double or multiple. Every time someone looked carefully at a spectrum that had previously been accepted as a single star's light, they risked finding that split line signature, that quiet Doppler confession of an unseen companion. This work was carried out largely by a group of women who rarely received the credit their contributions deserved. At Harvard, under the direction of Edward Pickering, a team of human computers women hired to analyze photographic plates of stellar spectra were doing the foundational work of stellar classification. Among them was a woman named Antonia Mori. Mori was Pickering's niece, and also by any measure one of the most talented stellar spectroscopists of her generation. Her classification scheme for stellar spectra was more nuanced and more physically meaningful than the one Pickering favored, and he largely dismissed it. It was Einar Hertzsprung, several years later, who recognized that Mori's categories corresponded to real physical differences between stars, specifically the difference between giant stars and dwarf stars. The classification system we use today incorporates the insights she developed. Her name is rarely mentioned in introductory astronomy courses, but her work and the work of her colleagues, Williamina Fleming, Annie Jump, Cannon, Cecilia Payne, and others, built the spectroscopic foundation on which our entire modern understanding of stars, including binary stars, rests. The women who mapped the stars did so with exceptional skill in conditions of institutional inequality that makes their achievements all the more striking. There's something important in that history. The most fundamental tool for understanding binary stars, spectroscopy, was refined and deployed largely by people who were systematically undervalued. The data that changed our picture of the universe was gathered by hands that the official record of science often forgot to mention. A common misconception worth addressing here: many people, when they first learn about spectroscopic binaries, assume that detecting them must be straightforward. Just look for stars with split spectral lines. But the reality is considerably more subtle. The splitting is only visible when the 2 stars are moving toward and away from us, when their orbital plane is oriented roughly edge-on to our line of sight. If the orbital plane is face-on with the stars circling each other in a plane perpendicular to our view, there's no net Doppler shift toward or away from us, and the lines don't split. The system is invisible as a binary by this method. This means that spectroscopic surveys almost certainly undercount the true number of binary systems. We can only detect the ones that happen to be oriented favorably relative to our position. The universe contains an unknown number of binary stars that have never announced themselves to our instruments circling each other in planes. We cannot measure in silence. We have no way to break. How many secrets does the sky still keep dressed up as simplicity? The history we've traced tonight, from the ancient assumption of optical doubles through Herschel's patient orbital measurements, through Pickering and Maury and the Harvard computers reading light into meaning, is a history of expanding imagination as much as expanding knowledge. Each step required someone to look at familiar data and resist the comfortable interpretation, to ask what if the obvious explanation isn't the right one, and that resistance, that willingness to sit with uncertainty rather than reach for the nearest reasonable answer, is not just a scientific virtue. It's a deeply human one, the kind of patience that allows you to look at something you think you understand and quietly ask whether you might be missing something. Because, as it turned out, spectroscopy was only the beginning. There was another way binary stars revealed themselves to careful observers, not through the language of light's color, but through the language of light's brightness. And this method would ultimately connect the quiet dance of binary stars to one of the most dramatic and consequential discoveries in the history of cosmology. The story of eclipsing binaries and the demon star Algol is waiting just ahead, and it carries within it a revolution in how we measure the universe itself. There is a point in space, invisible, unmarked, carrying no light of its own, that sits somewhere between two stars in a binary system. It has no name that most people know. It produces no radiation. No telescope has ever photographed it directly. And yet, every single moment, both stars in the system are in perfect obedience to it, circling it, bowing to it, organizing their entire existence around it. That point is called the barycenter, and understanding it changes everything about how you see the night sky. Most of us grew up with a picture of orbital motion that looks like this: a small thing going around a big thing. The moon circles the Earth circles the sun, smaller orbits larger. This is the image in every textbook, every classroom poster, every childhood explanation of how the solar system works. And it is, in a quiet but important way, incomplete. The truth is that no object ever truly orbits another object. What actually happens is that both objects orbit their common center of mass, their barycenter, simultaneously. Always. Without exception. The reason the textbook picture isn't entirely wrong is that when one object is vastly more massive than the other, the barycenter falls very close to the center of the larger object, sometimes even inside it. The sun is so much more massive than the Earth that their shared barycenter is buried deep within the sun's interior, which is why it looks, to a reasonable approximation, like Earth orbits the sun, rather than both orbiting a shared point. But the shared point is real. The sun wobbles. Slightly, almost imperceptibly, but it wobbles. It is not standing still while the Earth circles it. It too is moving, tracing a tiny arc around a center of mass that nobody thinks to mention in elementary school. Now, apply that same logic to two stars of comparable mass, and the picture transforms completely. When both stars are roughly equal in size and weight, their shared barycenter sits roughly in the middle of the space between them. And both stars trace orbits of roughly equal size around that central point, like two dancers of the same height, each leaning back slightly arms-length, spinning together around a shared axis that neither of them owns alone. This is not a metaphor chosen for poetic effect. The physics genuinely resembles a waltz. The elegance is real, and the moment you internalize it, the moment you replace the image of small thing orbiting big thing with two things orbiting a shared invisible point, you begin to see the universe with slightly different eyes. Let's make this concrete with a system you can actually find tonight. The brightest star in the southern sky, visible from anywhere in the southern hemisphere and from much of the northern hemisphere in late winter, is Sirius. That brilliant white point, the first star to emerge in a clear evening sky. The one that blazes so intensely it sometimes seems to flicker like a flame. Sirius has been revered across cultures for millennia. The ancient Egyptians aligned the orientation of certain temples to mark its heliacal rising the moment each year when Sirius first becomes visible just before sunrise after a period of invisibility. That moment coincided with remarkable reliability with the annual flooding of the Nile. Sirius was not just a star to the ancient Egyptians, it was a calendar, a warning, a promise of water and renewal. What the ancient Egyptians did not know what no one knew until 1862 is that Sirius is not alone. Orbiting Sirius at a distance of roughly 20 astronomical units, about the same as the distance from the Sun to Uranus, is a small, dense, extraordinarily dim companion star. We call it Sirius B, and Sirius B is one of the most scientifically important objects in the night sky, even though you cannot see it without a substantial telescope, and even then it is almost overwhelmed by the glare of its brilliant companion. The discovery of Sirius B is itself a beautiful story in two acts. In 1844, the German astronomer Friedrich Bessel was analyzing the proper motion of Sirius, its slow, gradual drift across the background of more distant stars over decades of observation. What Bessel noticed was that Sirius didn't drift in a straight line. It wobbled, a slight sinuous deviation from a straight path, repeating with a period of roughly 50 years. Bessel concluded that Sirius must have an unseen companion, a star massive enough to pull Sirius gravitationally, making both of them orbit their shared barycenter as they drifted together through space. This was 1844. The companion itself wasn't seen until 1862, when the American telescope maker Alvin Graham Clark was testing a newly built refractor, at the time the largest in the world, and spotted a faint point of light right next to Sirius, almost invisible in the glare. The object Bessel had predicted through mathematics alone, purely from the wobble in Sirius's path, was confirmed by direct observation 18 years later. This is worth savoring for a moment. An astronomer in 1844, without seeing Sirius B, without any instrument capable of detecting it, directly deduced its existence purely from the gravitational perturbation it caused in the motion of its companion. The invisible announced itself through its influence on the visible. The unseen was inferred from the behavior of the seen. This is in a very deep sense what much of modern astrophysics does, and Bessel was doing it in 1844. Sirius B turned out to be far more interesting than anyone initially expected. A white dwarf, the collapsed remnant of what was once a star, considerably more massive than our Sun, it packs a mass roughly equal to our Sun into a volume roughly the size of Earth. A teaspoon of its material would weigh approximately 5 tons. Its surface temperature is around 25,000 Kelvin, far hotter than Sirius A, which glows at about 10,000 Kelvin. And yet, Sirius B is nearly 10,000 times dimmer because it's so small. Temperature tells you how bright a surface is per unit area, but total brightness luminosity depends on both temperature and size. Sirius B is hot but tiny, a raging fire in a very small furnace, and it orbits Sirius A with a period of almost exactly 50 years, which means that right now as you listen, Sirius A and Sirius B are tracing their slow waltz around a barycenter that sits much closer to Sirius A, because Sirius A is roughly twice as massive. The dance is not symmetric. Sirius B traces a larger arc. Sirius A moves less. But both are moving. Both are in orbit. And the center of their shared dance sits in empty space between them, marking the gravitational heart of the system. Let's pause on that image because it contains something that is easy to miss. The barycenter of the Sirius system is not a star. It's not anything material. It's just a location, a mathematical point defined by the masses and positions of the two stars. It has no substance. It emits no light. It cannot be touched or photographed. And yet it has governed the motion of two stars for billions of years. Every orbit Sirius A and Sirius B have ever completed has been an orbit around that invisible, massless, real point. There's a philosophical resonance here that seems worth noticing, the idea that sometimes the thing that organizes an entire system, that determines the motion of everything within it, is itself invisible and intangible. The center of the dance is not the dancer. Now the shape of the orbits in a binary system depends on several factors, and this is where the orbital mechanics begin to reveal their full complexity. Binary star orbits are not necessarily circular. In fact, perfectly circular orbits are the exception rather than the rule. Most binary pairs follow elliptical paths, stretch circles more elongated for some systems, nearly circular for others. The degree of elongation is described by a number called eccentricity. An eccentricity of 0 means a perfect circle. An eccentricity approaching 1 means a very stretched, very elongated ellipse. High eccentricity binary orbits produce something fascinating and slightly dramatic. At the closest point in their orbit, called periastron, the two stars sweep past each other relatively quickly, sometimes at remarkably close range gravitationally, tugging at each other, potentially distorting each other's shapes slightly into subtle tidal bulges. Then they swing outward to their farthest point, a pastron moving slowly, almost lazily, before curving back inward for the next close approach. The variation in speed around an elliptical orbit follows a law that Kepler established in 1609. A star moves faster when closer to its companion, slower when farther away. The same law governs planets around the sun. The same law governs the moon around the Earth. And it governs binary stars around each other across every scale in every corner of the galaxy. Here is a misconception worth addressing gently because it comes up frequently. Many people, when they first encounter the concept of binary stars, imagine that the two stars must be very close together, that binary implies proximity. The image that comes to mind is often something like a contact binary, two stars nearly touching. But binary systems span an almost incomprehensible range of separations. Some contact binaries do indeed share their outer layers, orbiting each other in hours. But some binary pairs are separated by distances measured in thousands of astronomical units, so far apart that one orbit takes millions of years. These are called wide binaries, and they present an interesting challenge at those extreme separations. The gravitational bond is so tenuous that other stars passing nearby can gradually disrupt it over billions of years. Wide binaries are, in a cosmic sense, fragile partnerships together, for now, but not necessarily forever. The most astonishing example of a wide binary that I find quietly moving is the Alpha Centauri system, our nearest stellar neighbors mentioned briefly before, but worth dwelling on now, with fresh eyes. Alpha Centauri A and Alpha Centauri B are a genuine binary pair orbiting their shared barycenter with a period of about 79 years and an average separation of roughly 23 astronomical units, comparable to the distance between the Sun and Uranus. Their orbit is moderately elliptical, meaning that at their closest approach, they're separated by about 11 astronomical units, and at their farthest, about 36. They have been dancing this particular waltz for somewhere around 6 billion years longer than our own solar system has existed. Alpha Centauri A is slightly larger and more luminous than our Sun, yellowish-white, calm, and stable. Alpha Centauri B is slightly smaller, a warm orange, a little dimmer. From Earth, they appear as a single bright point, the third brightest star in the night sky, visible beautifully from the southern hemisphere. Only a telescope reveals that this point of light is actually two stars close enough in their orbit that they have been mistaken for one for most of human history. And here is a question that planetary scientists have spent considerable effort investigating. Could there be planets in the Alpha Centauri system? Could worlds orbit one or both of those stars? The answer based on current understanding is complicated. In a binary system, the gravitational influence of the companion star creates zones of stability and instability for orbiting planets. Planets in orbits much smaller than the binary separation, closely hugging one star, can be stable for long periods. Planets in orbits much larger than the binary separation, circling both stars together in what astronomers call circumbinary orbits, can also be stable. But planets in intermediate orbits in the gravitationally turbulent zone between the two regimes tend to be ejected or destabilized over relatively short timescales. For Alpha Centauri, The calculation suggests that stable orbits around Alpha Centauri, A or B, individually are possible within certain distance ranges. Whether actual planets exist, there remains an active area of research complicated by the technical difficulty of detecting planets in systems where the combined light of two stars makes the small signals of planetary transits and radial velocity wobbles harder to extract. But the possibility is real. And if a planet does exist in a stable orbit around one of the Alpha Centauri stars within its habitable zone, at the right temperature for liquid water, then from the surface of that world, the sky would contain something extraordinary. In addition to the warm, familiar light of the star it orbits, it would see the other member of the binary system as a brilliant second sun, not the hazy, uncertain twin of a distant pair, but a genuinely bright stellar presence. Not bright enough to read by at night if it's far enough away, but bright enough to cast shadows, bright enough to be unmistakable, bright enough to have shaped, one might imagine, whatever eyes ever evolved to look up at it. Do you ever find yourself wondering what the sky looks like from another world? From a place where the geometry of the solar system is different enough that all the familiar intuitions about day and night, about the rising and setting of suns, would simply not apply? Alpha Centauri offers one version of that imagined sky. A world around a binary star pair offers something different again. And we'll look at the specifics of that later tonight when we explore what science has actually confirmed about planets that orbit not one, but two stars simultaneously. For now, let's stay with the mechanics just a moment longer, because there is one more aspect of binary star orbits that is worth understanding, and it connects directly to the next surprising chapter in this story. When two stars orbit each other, they don't just exchange gravity, they exchange information about each other in the language of light and time, specifically in systems where the orbital plane is oriented edge-on to our line of sight, where one star periodically passes in front of the other. From our perspective, the light we receive from the system dims and brightens with extraordinary regularity. The orbit becomes, in effect, a clock. And that clock turns out to be one of the most precise measuring instruments astronomers have ever had access to. These are the eclipsing binaries, the systems where the dance becomes visible not as orbital motion, but as rhythmic dimming. And the most famous of them all is that ancient unsettling star we've already met, once Algol, the demon star of Perseus, whose mysterious winking tormented ancient observers for thousands of years. The solution to Algol's mystery and what that solution revealed about the nature of stars themselves is a story that leads somewhere none of the original investigators expected, directly into questions about how stars are born, how they age, and how a star can appear to be younger than its companion when the two were born at exactly the same moment. Imagine receiving a letter with no return address, no signature, no name, but written in a language so precise, so specific, that if you know how to read it, truly read it, you can identify exactly who wrote it, how fast they were moving when they wrote it, and whether they were coming toward you or walking away. That is almost exactly what starlight does. And the people who learned to read that letter changed astronomy forever. We left off at the edge of something, the promise that Algol's mystery would be solved, not by watching the star move across the sky, but by analyzing the light it sends us. That promise belongs to a field called spectroscopy. And while we touched on it briefly in part 2, what we're going to explore now goes deeper into the specific mechanics of how spectral analysis cracked open the interior life of binary stars in ways that no telescope pointed at the sky could ever achieve alone. Before we drift into that, if the quiet depth of these stories brings you something, a little wonder, a little peace at the end of the day, you're warmly welcome to press the like button and subscribe if you haven't yet. It costs nothing, and it means everything to a channel like this one. Now, let's continue. The story of spectroscopy and binary stars begins as so many beautiful stories in science do, with someone noticing something that wasn't supposed to be there. Something small, something easy to dismiss, something that, if you were in a hurry or working to a predefined agenda, you might simply overlook. In the early 1880s, astronomers at the Potsdam Observatory in Germany began systematically measuring the radial velocities of stars, their speeds toward or away from Earth, using the Doppler shift of their spectral lines. The principle, as we covered before, is elegant light. From a source moving toward you gets compressed into slightly shorter wavelengths, shifting toward the blue end of the spectrum. Light from a source moving away gets stretched into slightly longer wavelengths, shifting toward the red. By measuring how far the dark absorption lines in a star's spectrum had shifted from their known laboratory positions, you could calculate the star's radial velocity with considerable precision. This was already remarkable. From a distance of dozens or hundreds of light years, you could determine how fast a star was moving along your line of sight. The cosmos was surrendering one of its secrets through nothing more than careful measurement of light. But what happened when astronomers turned this technique toward Algol, that ancient winking demon star of Perseus, was something they hadn't fully anticipated. In 1889, the German astronomer Hermann Vogel at Potsdam obtained a series of spectroscopic observations of Algol timed around its brightness minimum, the moment when the star dimmed most deeply. And what he found confirmed with elegant precision what a young English amateur astronomer had proposed more than a century earlier. That amateur was John Goodricke, and his story deserves to be told fully because it is one of the most quietly moving in the history of science. John Goodricke was born in 1764 in Groningen, in what is now the Netherlands, to an English family. At the age of 5, he contracted a severe fever, scarlet fever. Most historians believe that left him profoundly deaf. He never recovered his hearing. He was educated at a school for the deaf in Edinburgh and later at Warrington Academy in England, where he proved to be exceptionally gifted in mathematics and natural philosophy. He moved to York as a teenager, and there he began observing the night sky with his neighbor and cousin Edward Pigott. In October 1782, when Goodricke was 17 years old, he began systematically monitoring Algol. He had noticed its variability, the periodic dimming that had troubled observers for centuries, and he set out to measure it precisely. Night after night, he recorded Algol's brightness timing, the minima calculating the period. By the end of 1782, he had determined the period with remarkable accuracy, approximately 2 days and 21 hours. And in a paper submitted to the Royal Society in 1783, he proposed 2 explanations for the variability. The first was that Algol had large dark spots on its surface, a kind of stellar equivalent of sunspots that periodically rotated into view. The second, which he stated with careful tentativeness, was something far more radical. Perhaps Algol was periodically eclipsed by a large dark companion body passing in front of it. Goodricke was 18 years old when he proposed the eclipse hypothesis for Algol. He could not hear the applause when the Royal Society awarded him the Copley Medal, one of the most prestigious scientific honors in Britain, for this work in 1783. He died in April 1786, 4 years later, at the age of 21, likely from pneumonia contracted during his nighttime observations. He never knew whether his eclipse hypothesis was correct. He never saw the confirmation that Vogel would provide more than a century later, but he was right. What Vogel's spectroscopic observation showed was this: as Algol approached its minimum brightness as the dimmer companion, star moved in front of the brighter primary. The spectral lines of the bright star shifted toward the red, indicating it was moving away from Earth. After minimum, as the companion moved past and the bright star's light returned, the lines shifted toward the blue, indicating the primary was now moving toward Earth. The velocity pattern was perfectly consistent with 2 stars orbiting each other, with the orbital plane oriented nearly edge-on to our line of sight. When the companion was in front, the primary was moving away from us. When the companion passed behind, the primary was approaching. The Doppler pattern was the orbital signature made visible in light. Goodricke's hypothesis, offered tentatively by a deaf 18-year-old in 1783, was confirmed spectroscopically in 1889. The eclipse interpretation was correct. Algol is an eclipsing binary, one of the first ever confirmed and still one of the most studied. But here is where the story deepens into something genuinely strange. Once astronomers confirmed that Algol was an eclipsing binary and began measuring the properties of both stars, their masses, their sizes, their temperatures, their luminosities, they found something that should have been impossible, something that broke the standard model of stellar evolution as astronomers understood it in the early 20th century. The two stars in the Algol system, Algol A and Algol B, are gravitationally bound. They formed at the same time from the same cloud of gas and dust, approximately 3 billion years ago. They are the same age. They must be. Stars in a binary system don't form at different times. They are siblings, born together from a common cradle. And yet, Algol B, the dimmer, cooler companion, is a subgent. It has already begun to evolve off the main sequence, swelling and changing in ways that suggest it is older and more evolved than its companion. Meanwhile, Algol A, the brighter primary, is still a healthy, stable, middle-aged main sequence star, showing none of the signs of advanced stellar age. This makes no sense if you assume that more massive stars age faster, which is exactly what stellar theory predicts. More massive stars burn their nuclear fuel more rapidly. They should evolve faster, become subgiants sooner, age more quickly than their lighter companions. In the Algol system, Algol A is the more massive star. It should be the more evolved one, but it isn't. Algol B, the less massive one, is the one showing signs of advanced age. The lighter star appears older. The more massive star appears younger. Astronomers called this the Algol paradox, and for decades it sat in the literature as an uncomfortable anomaly, a system that broke the rules that didn't fit the models that resisted clean explanation. The resolution when it came was one of those moments in science that completely reframes everything you thought you understood. The key was mass transfer, the very process that we will explore in depth in the next section of our journey tonight. But let's introduce the concept here because understanding how spectroscopy revealed it is essential to the story. As measurements of Algol B improved as spectroscopic techniques became more precise, and the properties of both stars were determined with greater accuracy, it became clear that Algol B currently fills what astronomers call its Roche lobe. The Roche lobe is an invisible boundary, a teardrop-shaped region around each star, in a binary system within which material is gravitationally bound to that particular star. If a star expands to the point where its outer atmosphere reaches the Roche lobe boundary, material at that boundary can flow across to the companion. It is, in a sense, the gravitational fence line between the two stars, and Algol B is right at that fence. The implication confirmed through increasingly sophisticated modeling through the mid-20th century was that Algol B had not always been the less massive star. Originally, it had been the more massive one. It evolved faster as theory predicted for more massive stars. It expanded off the main sequence, first becoming a subgiant. And as it expanded, it reached its Roche lobe and began transferring mass to its companion. Over millions of years, Algol B shed so much of its own material onto Algol A that the mass ratio reversed completely. The originally more massive star became the less massive one. The originally less massive star, now fattened on transferred material, became the brighter, more massive primary. The Algol paradox wasn't a paradox at all. It was evidence of a process that nobody had fully considered. That binary stars don't just influence each other gravitationally from a distance in a stately and non-contact dance. Under the right conditions, they physically exchange material. They reshape each other. They alter each other's evolutionary destiny in ways that would be completely impossible for an isolated single star. This is the deeper truth that spectroscopy unlocked, not just the orbital parameters of binary stars, not just their velocities and separations, but the evidence of intimate physical interaction that changes what a star is and what it will become. Think about what this means in the most human terms imaginable. Two stars born together, growing up together, orbiting each other in the dark. And over billions of years, one of them, the one that grows faster, The one that expands first begins to give itself away. Not violently, not catastrophically, just slowly, steadily, across millions of years, streaming its outer layers across the invisible gravitational boundary to its companion, diminishing itself, enriching the other. And in doing so, it changes both of them permanently. Now, spectroscopy revealed all of this, not by photographing the mass transfer stream directly, not by watching the process in real time. We couldn't. It happens on timescales of millions of years, but by reading the accumulated signature of the process in the light that both stars emitted. The masses were wrong for their evolutionary states. The orbital period was changing subtly over time, consistent with mass redistribution. The spectrum of Algol B showed the chemical fingerprints of a star that had lost its outer hydrogen-rich layers. Every clue was written in light. Every answer came from the spectrum. Here is a question worth letting settle slowly. How much of what you know about yourself came not from direct observation of the deep interior, but from reading the surface signals that interior processes left behind? Spectroscopy, in a sense, does. For stars, what careful listening does for people. It can't see inside, but it can read what the inside has written on the surface in temperature, in velocity, in chemical composition, in the subtle shifts of spectral lines that carry the whole history of a star's life encoded in color. The range of what spectroscopy has revealed about binary stars extends far beyond Algol. By the early 20th century, spectroscopic surveys had identified hundreds of binary systems, and astronomers began to notice patterns in the data that told a larger story about stellar populations. Binary systems with short orbital periods, systems where the stars are close together, showed systematically different spectral characteristics than wide binaries. Close binaries showed evidence of tidal distortion, where the gravity of each star pulls the other into a slightly elongated shape, like two balls of dough being slowly kneaded toward each other. In some systems, the stellar rotation had been synchronized to the orbital period by tidal forces, so that each star always showed the same face to its companion, the way our moon always shows the same face to Earth, tidally locked. Gravitationally intimate in a way that changes both stars' rotation, their magnetic fields, their activity levels, their long-term evolution. The diversity was dizzying. And in that diversity, a classification scheme began to emerge different types of binary systems, defined not just by their orbital parameters, but by the degree of physical interaction between the stars. We touched on these categories in our outline, but here seen through the lens of what spectroscopy actually measures, they take on concrete physical meaning. Detached binaries. Two stars orbiting each other, with both comfortably within their Roche lobes, not exchanging mass, evolving largely independently, but gravitationally bound. Semi-detached binaries like Algol, where one star fills its Roche lobe and is transferring mass to the other, and contact binary systems, where both stars overflow their Roche lobes, sharing an outer envelope of gas in a single peanut-shaped structure that is simultaneously one object and two. Each category represents not just a different configuration, but a different chapter in a binary system's life story. And the transition from one category to another, from detached to semi-detached to contact, is driven by the inexorable process of stellar evolution, playing out across timescales so vast that no human civilization will ever observe more than an infinitesimal fraction of any single system's journey. There's a particular contact binary system called W Ursae Majoris, visible with a small telescope in the constellation Ursa Major, that has been studied extensively because of how extreme its configuration is. The two stars in this system are so close, sharing so much of their outer envelope, that they orbit each other in just over 8 hours. 8 hours, not years, not months, not days, hours. The orbital velocity required to maintain that orbit at that separation is extraordinary, and the system is slowly losing angular momentum through a process involving magnetic stellar winds, which means the two stars are gradually spiraling closer together. In some hundreds of millions of years, they will likely merge entirely, forming a single rapidly rotating star fused from two stellar mergers, two stars becoming one. It sounds like the ending of a story, but as we'll discover, it's sometimes the beginning of something far stranger. The tools that spectroscopy gave us the ability to measure velocities, compositions, masses, and evolutionary states of stars, we cannot even visually resolve, as separate objects remain foundational to everything we know about binary stars today. Modern space-based observatories use the same Doppler principles that Vogel applied at Potsdam in 1889, refined now to detect velocity shifts of meters per second rather than kilometers, sensitive enough to find not just stellar companions, but planetary ones. The technique that revealed Algol's eclipse Sirius B's existence and the solution to the Algol paradox is the same technique that has found thousands of exoplanets orbiting distant stars. The light has always been trying to tell us something. The question is always whether we've developed the patience and the instruments to listen. And speaking of things the light reveals, there is one more layer to the Algol story that we haven't touched yet. One that connects the quiet rhythmic dimming of an eclipsing binary to one of the most extraordinary measurement tools in the history of cosmology. Because eclipsing binaries don't just tell us about the stars themselves. With the right mathematics, they tell us how far away those stars are, with a precision that no other method can match for certain distance ranges. And that precision applied carefully contributed to one of the most shocking discoveries in 20th century astronomy, that the universe is not just expanding, but accelerating. That thread from a winking demon star in Perseus to the accelerating expansion of everything is where the eclipsing binaries and their orbital geometry lead us next. There is a pair of stars in the constellation Lyra, the small, elegant constellation anchored by Vega, one of the brightest stars in the summer sky, that has a name almost no one outside of astronomy knows, and a nature that almost no one would guess from looking at it. It is called Epsilon Lyrae, and on a clear night with reasonably sharp eyes, you can split it into two faint points of light, sitting very close together. Two stars. A visual double. Nothing remarkable at first glance. But point even a modest telescope at Epsilon Lyrae, and each of those 2 points splits again into two more stars. What looked like two is actually four. Two pairs of binary stars, each pair orbiting its own internal center of mass, and both pairs orbiting each other in a vast, slow, gravitationally complex quadruple system. Astronomers call it the double-double, and it sits there quietly in the summer sky, four stars playing out, four simultaneous orbital relationships every single night, whether anyone is watching or not. The universe, it turns out, does not favor simplicity. It favors company. We have been moving through the history of how binary stars were discovered, measured, and understood. We have seen how gravity revealed them through wobbles, how light revealed them through spectral shifts, and how the Algol paradox cracked open the concept of mass transfer between stars. But we haven't yet taken a full, careful look at the sheer variety of what binary star actually encompasses, because the term covers a range of configurations so different from each other that calling them all by the same name sometimes obscures more than it illuminates. If these quiet journeys through the cosmos bring you something worth staying for, a gentle like and a subscription keeps this channel alive, and it means the next night, like this one, can find its way back to you. Now, let's keep drifting. Let's begin with a distinction that trips up even reasonably well-informed people: the difference between an optical double and a true binary. An optical double is two stars that happen to lie in nearly the same direction from Earth, but are actually at completely different distances, sometimes hundreds of light years apart, with no gravitational connection whatsoever. They are neighbors only in the sense that two strangers photographed in the same city are neighbors. Sharing a frame doesn't mean sharing a life. A true binary, by contrast, is two stars physically bound by gravity, orbiting their shared center of mass, moving through space together as a gravitationally coupled system. The distinction sounds obvious when stated plainly, but through a telescope eyepiece, an optical double and a close true binary can look identical. Separating them requires either precise measurement of the star's distances, which became possible only with the development of accurate parallax techniques, or long-term monitoring of their positions to determine whether they show orbital motion or merely drift independently. This distinction matters more than it might seem, because for much of the 18th and early 19th centuries, catalogs of double stars were filled with a mixture of true binaries and optical doubles without any reliable way to tell them apart. The numbers astronomers quoted for the frequency of binary stars were accordingly unreliable, either inflated by optical doubles that didn't belong, or deflated because subtler binary systems were missed entirely. It was only with improved distance measurements, better proper motion in surveys, and eventually space-based astrometry, particularly the Hipparcos satellite in the 1990s and the Gaia mission beginning in 2013, that astronomers began to get genuinely clean statistics on binary frequencies. Gaia, in particular, has transformed the field. By measuring the positions, motions, and distances of over 1 billion stars with extraordinary precision, Gaia has revealed vast populations of binary systems that were invisible to earlier surveys, wide binaries separated by tens or hundreds of thousands of astronomical unit systems that move through the galaxy together like quiet companions who never needed to be close to know they belong together. The numbers from Gaia suggest that binary fractions among stars vary significantly with stellar mass among the most massive stars. The hot blue O and B-type stars, binary fractions may exceed 70 or even 80%. Among sun-like stars, somewhere around 40 to 50%. Among the smallest, coolest red dwarf stars, perhaps only 20 to 30%. The more massive a star, the more likely it is to have company. Why? The answer likely lies in star formation, in the physics of how collapsing gas clouds fragment and form multiple cores. More massive stars tend to form in denser, more turbulent regions of molecular clouds, where fragmentation into multiple cores is more likely. Less massive stars often form in quieter, less turbulent environments, where a single collapsing core is more common. The birthplace shapes the outcome. The neighborhood you're born into determines to a significant degree whether you will spend your life alone or accompanied. There is something in that which resonates beyond astrophysics if you let it. Now, let's turn to the classification of true binary systems, not just by detection method as we discussed before, but by the physical relationship between the two stars, because this is where the real diversity lives. The most fundamental classification divides binary systems by the degree of physical interaction between the component stars, specifically by how each star's size relates to its Roche lobe, that invisible gravitational boundary we introduced when discussing Algol. In a detached binary, both stars sit comfortably inside their own Roche lobes, not filling them, not overflowing them. The stars evolve largely independently, each following its own internal clock, only occasionally perturbed by tidal forces from its companion. Most wide binaries and many close binaries are detached systems. Alpha Centauri A and B, orbiting each other at distances of 11 to 36 astronomical units, are a detached binary. The stars are separated enough that their individual Roche lobes are large relative to the stars themselves, and there is no mass transfer occurring. They are companions in the deepest sense, gravitationally bound, moving through space together, but physically independent, each burning its own fuel at its own rate. A semi-detached binary is a system where one star has evolved to the point where it fills its Roche lobe. At that boundary, material from the outer atmosphere of the larger star flows across to the companion, not in a steady, smooth stream, but through a specific point in space called the inner Lagrange point, the place where the gravitational pulls of the two stars exactly cancel each other. Material at this point is in an unstable equilibrium, a gravitational saddle, and can flow either way with the slightest perturbation. In practice, when one star expands to fill its Roche lobe, material streams across this point in a continuous flow, forming an accretion disk around the companion as it spirals inward. Algol, as we established, is the prototype of this class. But there are thousands of semi-detached binaries known, and each one is a system in active, ongoing transformation. A contact binary is the most intimate configuration, a system where both stars overflow their Roche lobes and share a common outer envelope of gas. The two stellar cores are distinct and separate, each still burning nuclear fuel independently, but they are surrounded by a single shared atmosphere, a peanut-shaped cloud of gas that connects them and allows energy and material to flow between them. Ursae Majoris, which we mentioned in the previous section, is the prototype of contact binaries, and the class is sometimes called WUMA-type systems in its honor. These systems are common enough that surveys suggest they account for roughly 1 in 500 stars in the solar neighborhood, more common than many people realize. Contact binaries raise interesting questions about what it means to be a single object versus two objects. The two stellar cores are distinct entities with distinct masses, distinct temperatures, distinct evolutionary histories. But their shared envelope forces them into a kind of thermal equilibrium. The energy generated by the hotter core is distributed across the common envelope and shared with the cooler core, so that the surfaces of both stars end up at nearly the same temperature, even though the cores may be significantly different. They are physically separate, but thermally connected. Two hearts, one skin. The eventual fate of many contact binaries is a stellar merger, the two cores spiraling together inside their shared envelope, releasing an enormous burst of energy and fusing into a single rapidly rotating star. Astronomers believe they have identified the observational signatures of such mergers in what are called red novae or luminous red novae, transient brightening events slower and redder than classical novae that appear to mark the moment when two stellar cores finally collide and unite. In 2008, a red nova erupted in the galaxy M85, briefly becoming visible in small amateur telescopes. In 2017, a red nova designated AT2017J FS blazed in the galaxy NG C4490. Each of these events may have been the visible signature of a stellar merger, a contact binary's final act, written across the cosmos in a brief, brilliant flare of red light. There is a particular stellar merger that astronomers are actually able to predict, not just detect after the fact, but anticipate in advance. The system is called KIC 9832227. Contact binary. In the constellation, Cygnus studied extensively because its orbital period has been measurably decreasing over time. When the orbital period of a contact binary decreases, it means the two stars are spiraling closer together, losing angular momentum, drawing toward the inevitable merger. In 2017, a team of astronomers published a paper predicting that KIC 9832227 would merge and produce a red nova sometime around 2022, give or take a year. That prediction attracted significant public attention. A specific datable prediction of a stellar explosion is a rare and exciting thing in astronomy. And then in 2018, the same team published a retraction. A re-examination of the historical data revealed an error in the calibration of older observations. The period decrease they had measured was not real. It was an artifact of bad data. The predicted merger was withdrawn. KIC 9832227. As far as current evidence suggests, is not about to explode. This episode is worth holding on to, not as an embarrassment, but as an illustration of how science actually works. A prediction was made. It was examined. An error was found. The prediction was revised. The system is more honest for it. The willingness to retract is not a weakness. It is the entire point. Beyond the three main interaction classes, detached, semi-detached, and contact, there are further subcategories based on the physical types of the stars involved, and these subcategories have profoundly different observational signatures and evolutionary outcomes. Consider X-ray binary systems, where one component is a neutron star or black hole, and the other is a normal star that is transferring mass to the compact object. As material from the normal star flows toward the neutron star or black hole, it forms an accretion disk and heats to temperatures of millions of degrees, emitting powerful X-rays. These systems are among the brightest X-ray sources in the sky, detectable across vast distances. The first confirmed stellar mass black hole, Cygnus X1, was identified in an X-ray binary system. The optical companion, a blue supergiant called HDE 226868, was found to be orbiting an unseen companion massive enough to be a black hole. The discovery of Cygnus X1 in the early 1970s settled what had been a genuine scientific controversy. Black holes were not just theoretical constructs, but real objects that could be identified through their gravitational effects on companion stars. Stephen Hawking famously made a bet with his colleague Kip Thorne in 1974 that Cygnus X1 was not actually a black hole, hedging his bets, he said, against the possibility that all his theoretical work on black holes would prove to have been a waste of time. By 1990, Hawking conceded the bet, acknowledging that the evidence had become overwhelming. He paid Thorne with a subscription to a magazine, as the terms of the bet required. And then there are the cataclysmic variables, a class of semi-detached binaries where the mass-receiving star is a white dwarf rather than a main sequence star. As material from the normal companion flows onto the white dwarf's surface, it accumulates until the pressure and temperature at the base of the accreted layer become high enough to ignite runaway hydrogen fusion. The result is a nova, a sudden dramatic brightening visible sometimes even to the naked eye, as the surface of the white dwarf detonates in a thermonuclear flash. Critically, the white dwarf itself survives this explosion. The detonation blows off the accreted layer, but the underlying white dwarf remains intact. And then the accretion begins again. The companion continues to transfer material. The layer builds up again. And in time, anywhere from decades to hundreds of thousands of years, another nova erupts. These are called recurrent novae, and they are among the most dramatic demonstrations of binary star interaction that the sky offers. A star that appears ordinary, even faint for years or decades, and then suddenly blazes, sometimes brightening by a factor of tens of thousands in a matter of hours or days, then slowly fading back to obscurity over weeks or months. The nova T Coronae Borealis, nicknamed the Blaze Star, erupted in 1866 and again in 1946. Astronomers monitoring its recent behavior have suggested it may be approaching another eruption based on observed changes in its brightness patterns. If it follows the same pattern it showed before its 1946 outburst, the next nova could bring it to naked eye visibility, briefly, dramatically, unmistakably, before fading once more into the dim catalog of ordinary stellar points. Have you ever looked up at a specific star and known, not just believed, but genuinely known, based on data, that it was about to do something extraordinary? That is what astronomers who study T Coronae Borealis live with. The star has told them something is coming. The timing is uncertain, but the announcement has been made in the quiet language of changing brightness. One more class of binary system deserves mention here, because it sits at the opposite extreme from the violent, eruptive, cataclysmic variables, and because it illustrates how the same basic configuration of two stars in mutual orbit can produce outcomes of almost infinite variety, depending on the masses, separations, and ages involved. These are the BY Draconis variables, close binaries composed of two cool, low-mass stars, often red dwarfs or late K-type stars orbiting each other, with periods of days to weeks. Their variability comes not from eclipses or mass transfer, but from star spots' dark magnetically active regions on their surfaces, similar to sunspots, but often far larger and more numerous, caused by the enhanced magnetic activity that results from the rapid rotation these close binaries maintain through tidal locking. As the spotted surfaces rotate into and out of view, the total brightness of the system changes slightly and periodically. The variability is subtle, a few percent at most, and the physics involved is in a sense the most ordinary possible. Star has spots. Star rotates, brightness changes. And yet, even in that ordinary process, there is a connection to something vast. The magnetic activity of closely orbiting stars is significantly higher than that of equivalent single stars, driven by the tidal synchronization of their rotation to their orbital period. High magnetic activity means stronger stellar winds, more intense flaring, higher levels of ultraviolet and X-ray emission. For any planets orbiting in the habitable zones of these magnetically active pairs, that heightened radiation environment may profoundly affect, perhaps preclude, perhaps merely complicate the development of life as we understand it. The question of life in binary systems, a question that once seemed purely speculative, the province of science fiction, rather than science, has become in the last decade an area of genuine and active research. And what astronomers have found is surprising in ways that the science fiction writers didn't always anticipate. That is where our journey takes us next, into the question of what it would actually mean to live under two suns, and whether the universe's preference for binary stars means that most potentially habitable worlds in the galaxy orbit not one star, but two. Picture a river that flows uphill, not because physics has been suspended, but because the landscape of gravity itself has been reshaped, tilted, warped, redirected by the presence of two massive objects pulling in competing directions. At a certain point between them, the two gravitational fields cancel each other out, and anything that reaches that point is balanced on a knife's edge, equally owned by both and committed to neither. And then the slightest nudge, the gentlest perturbation, sends it flowing one way or the other, irreversibly like water, finding a crack in a dam. This is not a metaphor. This is the actual physics of what happens when one star in a binary system expands enough to reach the gravitational boundary between itself and its companion. And what follows the slow, steady million-year river of stellar material flowing from one star to another is one of the most transformative processes in the universe. It changes what stars are. It changes what they become. And in some cases, it produces objects so strange, so unexpected, so contrary to every prediction of standard stellar evolution that astronomers had to invent entirely new categories just to describe them. We touched on mass transfer in Part 4 when we resolved the Algol paradox. But what we explored there was just the edge of the concept, the evidence that it had occurred, the reversal of mass ratios it produced. Now we go deeper, into the mechanics, into the consequences, into the objects that mass transfer creates that could never exist any other way. If you've been settling in gently with us through these hours, you're warmly welcome to press the like button and subscribe if the spirit moves you. It helps more than you might imagine, and it ensures that the next quiet night of science can find its way back to you. Now, let's drift further in. The concept of the Roche lobe takes its name from Édouard Roche, a French mathematician who, in 1849, calculated the gravitational geometry of a two-body system with extraordinary care and precision. Roche was not primarily an astronomer. He was a mathematician interested in the theoretical problem of how a fluid body held together by its own gravity, a liquid moon, or a gaseous stellar envelope would behave when subjected to the tidal forces of a nearby massive companion. His calculations showed that for every two-body gravitational system, there exists a critical surface now called the Roche surface, or Roche lobe, that defines the region within which material is gravitationally bound to each individual body. Roche's work was originally applied to the question of why Saturn's rings exist as rings, rather than coalescing into a moon. He calculated that within a certain distance of Saturn, now called the Roche limit. The tidal forces exerted by Saturn on any orbiting body would exceed the gravitational self-attraction of that body, preventing it from accreting into a coherent object. Rocks and ice within the Roche limit stay as rings. Outside it, they can accrete into moons. It is the same mathematical framework applied at a different scale that governs mass transfer in binary stars. The inner Lagrange point, the specific location on the Roche lobe boundary where mass transfer begins, was identified by Joseph Louis Lagrange in 1772 as one of 5 special points in any two-body gravitational system, where a small third body can orbit in a fixed position relative to the 2 larger ones. These 5 Lagrange points have found extraordinary practical applications in modern astronomy and space science. The James Webb Space Telescope orbits the Sun, Earth L2. Lagrange point a location about 1.5 million kilometers from Earth, directly opposite the Sun, where the combined gravitational and centrifugal forces keep the telescope in a stable position relative to Earth. The same mathematical framework that describes where stellar material begins to flow in a binary system also describes where we park our most powerful astronomical observatories. The universe reuses its mathematics with breathtaking economy. Now, when material begins flowing across the inner Lagrange point from the donor star to the accretor, the star receiving the transferred mass, it doesn't fall directly onto the accretor's surface. It carries angular momentum, a measure of its rotational motion, from the original orbit of the donor star. This angular momentum prevents it from falling straight in. Instead, the transferred material spirals inward around the accretor, forming a flattened rotating disk of gas called an accretion disk. The material in the disk moves at different speeds at different radii, faster close to the accretor, slower farther out. And these velocity differences generate friction, which heats the gas, which causes it to radiate energy and gradually spiral inward. Eventually, after losing enough angular momentum to friction within the disk, the gas reaches the surface of the accretor and is deposited there. This process, accretion through a disk, is one of the most efficient energy-releasing mechanisms in the universe. For ordinary stars accreting onto white dwarfs or neutron stars, the gravitational potential energy released as material falls into the deep gravitational well of the compact object, can equal or exceed the energy released by nuclear fusion in the donor star itself. Accretion disks around neutron stars and black holes are among the most luminous objects in the X-ray sky, as we noted in our discussion of X-ray binaries. But even in more ordinary stellar binaries where the accretor is a main sequence star rather than a compact remnant accretion, disks form glow and leave their signature in the spectrum of the system. What does mass transfer actually do to the 2 stars involved? The answer differs depending on which star you're asking about. For the donor star, the one losing mass, the effects are in some ways counterintuitive. You might expect that losing mass would make a star cooler and dimmer simply because there's less of it. And in some respects, that's true. The donor star shrinks, cools, and becomes less luminous as it loses its outer layers. But the time scale and manner of that shrinkage depend critically on the rate of mass loss. If mass transfer happens slowly on timescales comparable to the star's own thermal adjustment time, the star can reach a new equilibrium at each stage, contracting gradually and cooling gently. If mass transfer is rapid faster than the star can thermally adjust, the star may actually expand in response to the mass loss, temporarily overshooting its new equilibrium size, which can cause the mass transfer rate to increase further in a runaway process. For the accretor, the star gaining mass, the situation is equally complex. A star that gains mass effectively rejuvenates itself. The additional hydrogen-rich material from the donor's outer layers supplements the accretor's own hydrogen supply, extending the time it can spend on the main sequence. More dramatically, the accreted material is deposited on the surface of the accretor with relatively low helium content. It came from the outer hydrogen-rich layers of the donor, not from the nuclear-processed interior. so the accretor ends up with a surface composition enriched in hydrogen relative to its interior. It looks in terms of its surface spectral characteristics younger and less chemically evolved than it actually is. This rejuvenation process produces one of the most visually striking anomalies in stellar astronomy, the blue straggler. In a star cluster, a gravitationally bound collection of stars that all formed at the same time from the same molecular cloud, you would expect the stars to form a clean sequence on a color magnitude diagram, with the most massive stars having already evolved off the main sequence, and the less massive stars still burning hydrogen quietly. The main sequence should have a well-defined turnoff point, the location where the most massive still surviving main sequence stars sit, marking the current age of the cluster. Blue stragglers are stars that appear in the color magnitude diagram above and to the blue side of the main sequence turnoff, exactly where you would not expect to find any stars, because stars of that mass should have evolved away long ago. They are, in a sense, stars that have cheated their own aging. They appear younger than the cluster they live in. Bluer, hotter, more luminous than the turn-off stars, they stand out like anomalies, like exceptions to the rule of stellar aging. The first blue stragglers were identified by Alan Sandage in 1953 in the globular cluster M3. Sandage noticed them and was puzzled. For decades, their origin was debated. Multiple explanations were proposed. Perhaps they formed later than the rest of the cluster from leftover gas. Perhaps they were the products of stellar mergers. Perhaps they were binaries caught in the act of mass transfer. The current consensus, supported by extensive observational and theoretical work, is that blue stragglers form through two primary channels: mass transfer in binary systems and direct stellar collisions and mergers. Both processes dump fresh hydrogen-rich material onto a star, pushing it back toward a hotter, bluer, more youthful appearance on the color magnitude diagram. In dense globular clusters, where stars are packed close enough together that direct collisions become statistically probable over billions of years, the collision channel may dominate. In less dense open clusters, where direct collisions are essentially impossible, mass transfer in binaries appears to be responsible for most blue stragglers. Astronomers can often distinguish the two origins by looking at the chemical composition of the blue stragglers. Spectrum collision products may show different elemental signatures than mass transfer products, depending on which layers of the colliding stars were mixed in the merger. Blue stragglers are not rare. Every star cluster that has been examined with sufficient sensitivity shows them. They are a ubiquitous consequence of the fact that stars live in communities, and communities involve interaction, and interaction in the stellar world, as in human ones, can profoundly alter an individual's trajectory. There is a specific blue straggler worth naming because it sits close enough to be studied in unusual detail. In the open cluster NGC 188, a relatively old cluster about 6,800 light-years away, in the constellation Cepheus, astronomers have identified a population of blue stragglers that appear to be preferentially found in binary systems, with long orbital periods roughly 800 to 1,000 days, and with companions that are likely white dwarfs. This pattern, blue stragglers, paired with white dwarfs on long-period orbits, fits neatly with a specific mass transfer scenario. The white dwarf is the evolved remnant of what was once the donor star. The binary originally contained a more massive star and a less massive companion. The more massive star evolved, first expanded, began transferring mass to its companion, rejuvenating it into a blue straggler. And then the donor eventually shed its outer layers entirely to become a white dwarf. The system is now a blue straggler orbited by the ghost of its benefactor, the depleted remnant of the star that gave it new life. There is something quietly moving about that image, a star that extends another's youth at the cost of its own substance. And what remains after the giving is done is not nothing. It is a white dwarf, dense and enduring, still present, still orbiting, still gravitationally connected to the star it transformed. Mass transfer doesn't always proceed gently, and it doesn't always produce rejuvenation. In some systems, particularly those involving neutron stars or black holes, the accreted material builds up under conditions so extreme that the outcomes are violent beyond almost any other natural process. We touched briefly on cataclysmic variables and their nova eruptions in the previous section. But there is a specific scenario, a specific threshold where accreted material on a white dwarf doesn't just trigger a surface nova, it triggers the complete catastrophic destruction of the white dwarf itself. This is the Type 1a supernova, and it is quite possibly the most consequential product of binary star interaction for our understanding of the cosmos. A Type 1. A supernova occurs when a white dwarf in a binary system accretes enough mass to approach a specific critical value, approximately 1.4 times the mass of our Sun. This threshold, known as the Chandrasekhar limit, after the Indian-American astrophysicist Subramanian Chandrasekhar, who calculated it in 1930, represents the maximum mass that a white dwarf can sustain against gravitational collapse through electron degeneracy pressure alone. Below the limit, a white dwarf is stable. Indefinitely, it can cool for billions of years without collapsing. Above the limit, electron degeneracy pressure can no longer support the star's weight, and collapse begins. But in a white dwarf made primarily of carbon and oxygen, which most white dwarfs are collapse triggers, something that collapse in a normal star does not. As the white dwarf contracts past the Chandrasekhar limit, the temperature and pressure rise to the point where carbon and oxygen fusion ignites not gently, not in a controlled gradual way, but in a runaway thermonuclear detonation that propagates through the entire star in a fraction of a second. The white dwarf does not collapse into a neutron star. It explodes, completely, utterly. Nothing remains. In a few seconds, a star that took billions of years to form releases more energy than the Sun will emit in its entire 10 billion year lifetime. The extraordinary feature of Type 1. Supernovae, the feature that makes them so cosmologically important, is their remarkable uniformity. Because they are all triggered by the same physical threshold, the Chandrasekhar limit, they all reach approximately the same peak luminosity. They are, in the language of observational astronomy, standard candles, objects whose intrinsic brightness is known well enough that their apparent brightness in our sky can be used to calculate their distance. By observing Type 1, a supernovae in distant galaxies, and comparing their apparent brightness to their known intrinsic luminosity, astronomers can measure cosmic distances with remarkable precision. In 1998, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, used Type 1, a supernova, to measure the expansion rate of the universe at different cosmic epochs. What they found shocked the astronomical community. The expansion of the universe was not slowing down, as gravity should cause it to do. It was speeding up. The universe was accelerating in its expansion, driven by some form of energy embedded in the fabric of space itself, an energy that has no known physical explanation, and that has been given the placeholder name dark energy. The discovery of dark energy, arguably the most profound and mysterious result in modern cosmology, rested critically on the precision of Type 1a supernova distance measurements. And Type 1a supernovae are products of binary star mass transfer. The slow, patient accumulation of stolen mass onto a white dwarf surface, gram by gram over millions of years, is what primes the detonation that illuminates galaxies across billions of light years and reveals the accelerating fate of the cosmos. We are here knowing what we know about the universe's ultimate destiny because stars and binary systems steal from each other. Have you ever considered how many of the largest truths about the universe were revealed not by studying the universe's grandest structures, but by paying careful, patient attention to the intimate relationships between pairs of objects that most people have never heard of? The blue stragglers quietly cheating their own aging, the white dwarfs accumulating stolen mass until they shatter the fundamental limits of their own existence. The accretion disks spinning in the darkness between stars, carrying away angular momentum and energy in forms we can detect from across the galaxy. Every one of these phenomena is a consequence of proximity of two stars being close enough to each other that their gravitational fields overlap. Their material intermingles, their evolutionary destinies become permanently, irreversibly entangled. And the most dramatic consequences of that entanglement, the most violent, the most energetic, the most cosmically significant, are still ahead of us. Because when mass transfer doesn't just rejuvenate a star or trigger a nova, but instead builds toward a catastrophe involving neutron stars and the very fabric of space-time itself, the outcome is something that Albert Einstein predicted, and that humanity didn't directly detect until 2015. An event so energetic that it stretches and compresses the geometry of space across 1 billion light years, arriving at Earth as a ripple smaller than 1,000th of the width of a proton, and yet detectable, measurable, real. The death duet of binary stars and the gravitational waves they leave behind is where we go next. On the 17th of August, 2017, at 12:41 in the afternoon, Universal Time, a signal arrived at Earth. It had been traveling for 130 million years. It originated in a galaxy called NGC 4993 in the constellation Hydra, at a distance so vast that the light-carrying news of the event had been en route since before the first dinosaurs walked on land. The signal was not light. It was not radio waves. It was not X-rays or gamma rays or any form of electromagnetic radiation at all. It was a ripple in the geometry of space itself, a gravitational wave stretching and compressing the very fabric of space-time as it passed through the Earth, through every atom of every human body, through the planet's molten core, through everything, without resistance, without friction, without pause. The detectors at LIGO in Louisiana and Washington State registered this ripple as a displacement smaller than 1/10,000th the width of a proton. And in the 100 seconds that followed, the gravitational wave signal, gamma-ray observatories in space detected a burst of the most energetic radiation in the universe arriving from the same direction. Then, over the following days and weeks, telescopes around the world watched a new point of light appear in NGC 4993 bright blue-white, at first then fading and shifting to red over days as the debris of the event scattered across space. Two neutron stars, each one the collapsed remnant of a massive star that had lived and died in a binary system, had been spiraling toward each other for hundreds of millions of years, losing energy to gravitational wave emission, drawing inexorably closer. And on that August afternoon, they had finally collided. The event was designated GW170817, and it answered in a single observation questions that astronomers had been asking for decades. The question of where gold comes from, where platinum comes from, where uranium comes from, where every element heavier than iron that exists in the universe, in your jewelry, in the circuits of the device you may be listening on, in the water you drank today was forged. The answer is, in moments exactly like the one that produced GW170817, in the collision of neutron stars and binary systems in a process called rapid neutron capture nucleosynthesis, the R process where atomic nuclei are bombarded with neutrons so rapidly that they build up into heavy elements before they have time to decay. The gold in your wedding ring, if you wear one, was made in a neutron star merger, perhaps one merger, perhaps several over billions of years, with the ejected material eventually incorporated into the molecular cloud that formed our solar system. The most precious metals in human culture are the debris of the most violent events in the universe produced by the final act of binary stars that dance together for 100 million years before their last embrace. Before we follow that thread all the way to its extraordinary end, a quiet word. If these long, slow nights of science bring you something worth returning to, a like and a subscription means more quiet nights can find their way to you. Thank you for being here. Now, let's go deeper. To understand how two neutron stars end up in a binary system in the first place, how this dance of death is set in motion, we need to go back to the beginning of the system, billions of years before the collision. Because the path from two ordinary stars to two neutron stars in a tight death spiral orbit is one of the most improbable seeming sequences of events in all of astrophysics. And yet it happens. It has happened billions of times in the history of our galaxy alone. It begins with a binary system containing two relatively massive stars, not the most massive in the galaxy, but substantial, perhaps 10 to 20 times the mass of the Sun, each burning hot and blue, consuming their nuclear fuel at a prodigious rate. Massive stars live fast and die young. While our Sun will spend roughly 10 billion years on the main sequence, a star 20 times as massive burns through its hydrogen in perhaps 10 million years, 1,000 times faster. So, in a binary system containing two such stars, the more massive one reaches the end of its main sequence. Life first begins to expand, potentially transfers mass to its companion, and eventually undergoes a core collapse supernova, a catastrophic implosion of the stellar core when nuclear fusion can no longer support the star's weight. The supernova of the first more massive star is by itself an event of almost incomprehensible violence. In less than a second, the iron core of the dying star, roughly the size of Earth, collapses to a sphere about 20 kilometers across. The density of this collapsed object, the neutron star, is so extreme that a single teaspoon of neutron star material would weigh approximately 4 billion tons. The collapse releases more energy in that single second than the Sun will radiate over its entire 10 billion year life. Most of that energy leaves as neutrinos, nearly massless, almost non-interacting particles that stream outward through the collapsing star and escape into space within seconds, carrying the bulk of the explosion's energy before the visible supernova light even begins. The outer layers of the dying star, rebounding from the collapsed core, are blasted outward in the visible supernova explosion, one of the brightest events in the universe, sometimes outshining the entire galaxy that contains it for days or weeks. What remains is a neutron star, dense, rapidly rotating, often emitting beams of radio waves from its magnetic poles that sweep across the sky like a lighthouse as the star spins. If one of those beams happens to point toward Earth with each rotation, we detect it as a pulsar, a source of radio pulses arriving with clockwork regularity, accurate enough in some cases to rival atomic clocks. Now here's the crucial and often overlooked question. What happens to the binary system when one of its stars explodes? The supernova ejects roughly half the star's mass or more in a fraction of a second. And this sudden mass loss has an immediate dramatic effect on the gravitational bond between the two stars. If more than half of the total system mass is ejected instantaneously, the gravitational binding energy of the binary drops below zero, the system becomes unbound, and the two stars fly apart, never to interact again. The neutron star and its companion scatter into space as independent objects, their former partnership dissolved by the violence of the explosion. For a binary system to survive the first supernova, to keep the neutron star and its companion gravitationally bound, several conditions must be met. The mass ejected must not be too large relative to the total system mass. The supernova must not give the neutron star too strong a velocity kick in a direction that breaks the orbit. And the orbital parameters, the separation and eccentricity, must be such that even after the sudden mass loss reshapes the orbit, the two stars remain bound, though typically in a more eccentric orbit than before. It is estimated that only a minority of binary systems survive the first supernova intact. Many are disrupted, their components scattered. The ones that survive do so by chance, by the specific combination of masses, orbital geometries, and kick directions that conspire to maintain the bond despite the violence. In the surviving systems, the neutron star and its companion, still a normal main sequence or evolved star, continue their orbital dance, now in a more eccentric orbit, the neutron star perhaps visible as a pulsar, the companion continuing to evolve. If the companion star is massive enough, it too will eventually exhaust its nuclear fuel, expand, potentially transfer mass to the neutron star, and ultimately undergo its own core collapse supernova. If this second supernova also fails to disrupt the system, another improbable but possible outcome. What remains is a binary neutron, star 2, collapsed stellar cores, each roughly 20 kilometers across, each containing roughly 4 solar masses orbiting each other in a tight eccentric orbit. The first binary neutron star system ever discovered was identified by Russell Hulse and Joseph Taylor in 1974 using the Arecibo radio telescope in Puerto Rico. The system designated PSRB 1913+16, also known as the Hulse-Taylor binary, consists of a pulsar and a companion neutron star. The pulsar's regular radio pulses allowed Hulse and Taylor to measure the orbital parameters of the system with extraordinary precision, tracking its motion through the Doppler shifts in the pulse arrival times. What they found over the following years was a confirmation of something Einstein's general theory of relativity had predicted 50 years earlier, but that had never been directly observed. A binary system in a close orbit should lose energy by emitting gravitational waves, ripples in space-time, and as a result, the orbital period should gradually decrease as the two neutron stars slowly spiral toward each other. Hulse and Taylor measured exactly this decrease with a rate that matched Einstein's prediction to within 0.5%. The orbital period was decreasing by about 76 microseconds per year. A tiny change, but measurable, consistent, and unmistakably real. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. They had proven the existence of gravitational waves indirectly through their effect on the orbit 2 decades before LIGO would detect them directly. The binary pulsar was, in a sense, a gravitational wave source that we could watch slowly advertising its own future catastrophe. The Hulse-Taylor binary will merge in approximately 300 million years. GW170-817 was a system that completed that journey, and what its merger produced is worth examining in detail because the observations made in August 2017 were unprecedented in their completeness and their implications. The gravitational wave signal from GW170817 lasted about 100 seconds, significantly longer than the signals from binary black hole mergers detected earlier, which lasted only fractions of a second. The difference in duration reflects the difference in mass neutron stars are less massive than the stellar mass black holes in previous detections, so they orbit more slowly at a given separation and take longer to complete the final in spiral. As LIGO and its European counterpart Virgo recorded the gravitational wave signal, the frequency of the waves increased steadily, what physicists call a chirp, as the neutron stars spiral closer and closer, and their orbital frequency increased until the moment of merger when the signal abruptly cut off. Approximately 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same direction in the sky. Short gamma-ray bursts, intense brief flashes of the most energetic electromagnetic radiation, had been observed since the 1960s. And had been theorized to result from neutron star mergers, but the connection had never been directly confirmed. GW170817 confirmed it. The 7-second delay between the gravitational wave merger signal and the gamma-ray burst is consistent with theoretical models in which the merger itself produces a millisecond magnetar or a black hole. The exact outcome is still debated, and the gamma-ray burst is produced slightly later as relativistic jets of material are launched from the merger remnant. In the days that followed, the optical and infrared observations of the merger site revealed what is called a kilonova, a transient brightening powered by the radioactive decay of freshly synthesized heavy elements in the ejected merger debris. The spectrum of the kilonova showed the unmistakable fingerprints of heavy R process element strontium was confirmed, and the overall brightness and color evolution was consistent with large quantities of lanthanide elements and gold. Estimates suggested that the merger ejected material containing gold, equivalent to perhaps 40 to 100 times the mass of the Earth. Platinum in comparable quantities. Dozens of other heavy elements scattered across space in the expanding debris cloud of a dead binary system. Let that settle quietly for a moment. The ring on your finger if you wear gold, the platinum in your catalytic converter, the iodine in your thyroid, the uranium in the Earth's crust that keeps its interior warm enough to sustain plate tectonics and volcanism, and the geological processes that regulate our climate. All of it, all of these heavy elements came from moments like GW1 70817, from neutron star mergers in binary systems scattered across space in kilonovae, incorporated into molecular clouds, condensed into planets, and ultimately assembled atom by atom into the world and everything in it, including you. You are, in the most literal chemical sense, the product of binary stars that died together. There is a misconception worth addressing here, because it comes up whenever neutron star mergers are discussed in popular science. Many people, having heard that heavy elements come from neutron star mergers, assume that supernovae are therefore not important for element production. This is not correct. Supernovae, particularly core collapse supernovae, are responsible for producing and distributing the elements from oxygen through iron, the building blocks of rocky planets of water, of biological molecules. The iron in your blood came from supernovae, not neutron star mergers. The oxygen you are breathing right now was produced in the cores of massive stars and scattered by their explosions. Supernovae and neutron star mergers are not competing explanations for chemical enrichment. They are complementary processes, each responsible for different portions of the periodic table, both essential to producing the chemical complexity that makes planets and life possible. The binary star system contributes to both channels. Core collapse supernovae are often the deaths of stars in binary systems their evolution shaped, as we've seen by mass transfer and tidal interaction with companions. And neutron star mergers require that two stars in a binary system both die as neutron stars and remain gravitationally bound through both deaths. The binary system is the vehicle. The violence is the engine, and the chemical richness of the universe is the product. One more thread deserves to be followed here, because it connects this cosmic chemistry to a question that has profound implications for the search for life elsewhere in the universe. The heavy elements produced in neutron star mergers are not instantaneously available for incorporation into new solar systems. After a kilonova, the ejected material must travel through space, disperse, cool, and eventually be swept up in the gravitational collapse of a new molecular cloud to form new stars and planets. This process takes time hundreds of millions to billions of years, and it means that the chemical inventory of any given region of the galaxy depends on its history of neutron star mergers, how many occurred, how long ago, how much material was ejected, and in what direction. Regions of the galaxy that have experienced more neutron star mergers will be more enriched in heavy elements. Stars that formed earlier in the galaxy's history, before many mergers had occurred, will have lower abundances of gold, platinum, and other R process elements. Stars that formed more recently in regions with a longer history of mergers will be richer in these elements. The distribution of heavy elements across the galaxy is not uniform. It is a chemical map of the galaxy's violent binary stellar history, written in the abundances of gold and platinum in stars and planets scattered across the disk of the Milky Way. Whether this distribution matters for life is an open question. Life as we know it does not require gold or platinum. These elements play no biological role. but the distribution of our process elements traces the distribution of all heavy elements generally, and some of those elements, iodine, selenium, molybdenum, do play roles in biological chemistry. A planet formed in a region very poor in our process enrichment might lack some of the trace elements that life as we currently understand it finds useful. The universe's chemistry shaped by the deaths of binary stars may itself be a factor in the distribution of life. The violence that ends binary systems ripples outward not just as gravitational waves and gamma rays, but as the atoms that will one day in some future solar system find themselves assembled into something that wonders where it came from. And now, having followed the death of binary stars all the way to the gold in your jewelry and the atoms in your body, the final question circles back to the living, to the planets still orbiting in binary systems that haven't yet reached their end, to the worlds beneath two suns, where perhaps something looks upward and wonders at the light. That question, can life exist in a binary system? And what would the sky look like from a world with two suns is exactly where we go from here. Imagine standing on a beach at the end of a day. The air is warm, the water is still. And on the horizon, two suns are setting, not simultaneously, not in the same place, but at slightly different angles, one dropping below the water's edge, while the other still hangs a few degrees above it, casting a second set of shadows across the sand that point in a direction just slightly different from the first. The sky between them is a color that has no name in any human language, a gradient that shifts from deep amber near the lower sun through a band of violet and into a pale rose, where the higher one still burns. You have two shadows. Both of them are yours. Both of them stretch in slightly different directions across the wet sand. And the light is unlike anything a single sun could ever produce, layered, complex, rich, in a way that is difficult to describe but immediately viscerally felt. This is not a scene from a novel. It is a scientifically plausible description of an evening on a world that astronomers have actually confirmed exists. A world that orbits not one star, but two. A world where the concept of a single clean sunset, the kind humans have watched for every evening of our entire species' existence, simply does not apply. That world is real, and it is not alone. If these gentle hours of science give you something worth carrying into sleep, you're warmly welcome to press the like button and to subscribe if you haven't already. Each one genuinely matters. Now, let's step onto that alien shore together. For most of the history of astronomy, the question of whether planets could exist in binary star systems was considered largely academic, interesting theoretically, but essentially untestable because detecting planets around even single stars was beyond the capabilities of the instruments available. The first confirmed detection of a planet orbiting a main sequence star came only in 1995 when Michel Mayor and Didier Queloz identified 51 Pegasi b, using the radial velocity method, the same Doppler spectroscopy technique we explored in earlier chapters of tonight's journey, refined now to detect the tiny stellar wobble caused by a planet rather than a stellar companion. Mayor and Queloz received the Nobel Prize in Physics in 2019 for this discovery. Once the detection of exoplanets became technically feasible, the question of planets in binary systems moved from theoretical to empirical very rapidly. And the answers that began coming back from space telescopes, particularly the Kepler Space Telescope launched in 2009, were in the best possible way surprising. The key discovery came in 2011, when a team analyzing Kepler data announced the detection of Kepler's 16Ba planet, orbiting not one, but both stars of a binary system. A circumbinary planet, a world whose orbit encompasses both stellar components circling the pair from a distance the way a planet might orbit the center of mass of the binary rather than either individual star. Kepler 16 consists of two stars, a K-type orange dwarf and a smaller M-type red dwarf orbiting each other with a period of about 41 days. Kepler 16b orbits the entire binary pair with a period of about 229 days, at a distance of roughly 0.7 astronomical units from the center of mass of the pair. The detection method was elegant. Kepler 16b was found through its transits the slight dimming of the combined light from the binary system as the planet passed in front of one or both stars. But unlike the regular, perfectly periodic transits of a planet around a single star, the transits of a circumbinary planet are irregular in timing and depth because the planet is orbiting a center of mass that is itself shifting as the two stars orbit each other. The pattern of transits is complex, almost musical in its layered rhythms, and it was precisely this complexity that allowed the Kepler team to confirm not just the planet's existence, but its orbital parameters in detail. George Lucas famously imagined Tatooine's twin sunset long before astronomers confirmed such worlds were real. When the Kepler 16b discovery was announced, the lead author of the paper, Lawrence Doyle of the SETI Institute, described the world as the real Tatooine, and the name stuck immediately in public imagination. Science fiction had intuited something that science was still developing the tools to verify. The intuition, it turned out, was correct. But Kepler 16b is not in the habitable zone of its binary system. It orbits at roughly the same distance as Venus from our Sun, but the combined luminosity of the two Kepler 16 stars is significantly less than the Sun's, so the effective temperature of Kepler 16b is estimated at around -100 degrees Celsius, far too cold for liquid water on its surface, and likely a gas giant without a solid surface anyway. It is not in the sense that matters for life, a habitable world. The question of habitability in binary systems is considerably more nuanced than a simple yes or no, and it's worth spending time on it carefully because popular treatments of this topic often oversimplify in both directions. Some sources suggest that binary systems are hostile to life because of the complex gravitational and radiation environments they create. Others suggest that with the right configuration, binary systems could be perfectly hospitable or even more favorable than single-star systems in some respects. The scientific reality, as usual, sits in the details. Let's begin with the gravitational stability question because it is foundational. For a planet to be habitable over the billions of years that complex life seems to require, based on Earth as our only data point, it needs to maintain a stable orbit in or near the habitable zone for a geologically and evolutionarily significant period. In a binary system, gravitational stability depends critically on whether the planet orbits one star closely in S-type or circumstellar orbit, or both stars, from a distance of P-type or circumbinary orbit. For S-type orbit stability analyses, show that planets can maintain stable orbits around one star in a binary system if the orbital radius of the planet is significantly smaller than the separation between the two stars, typically less than about 1/5 to 1/3 of the binary separation. If the two stars in the binary are separated by, say, 20 astronomical units, a planet could potentially maintain a stable orbit within about 4 to 6 astronomical units of one of the stars. For Sun-like stars, the habitable zone sits between roughly 0.95 and 1.7 astronomical units from the star well within the stable zone, for a binary separation of 20 astronomical units. The companion star at 20 astronomical units would be present in the sky, visible, possibly bright, but its gravitational influence on the planet would be a modest perturbation rather than an orbit-disrupting force. For P-type orbits circumbinary planets like Kepler 16, B stability requires that the planet orbit far enough outside the binary pair that the complex time-varying gravitational field of the two orbiting stars doesn't destabilize the planet's orbit. For most binary pairs with orbital periods of days to weeks, stable circumbinary orbits exist outside roughly 2 to 4 times the binary separation. A circumbinary planet in the habitable zone of a binary system is therefore possible if the binary pair is close enough short, orbital period, small separation, that the inner edge of the stable circumbinary zone sits within or near the habitable zone defined by the combined luminosity of both stars. This is exactly the configuration that makes circumbinary habitability possible. A compact binary, two stars orbiting each other in a few weeks or less, presents a combined luminosity that defines a habitable zone at a certain distance, and the stable circumbinary orbital region extends close enough to that zone to overlap with it. Kepler 47, CEA gas giant in the Kepler 47 binary system, actually orbits within the habitable zone of its binary pair, though it too is a gas giant and not a candidate for surface life, as we understand it. But the orbital mechanics demonstrate that the habitable zone and the stable circumbinary zone can overlap. Beyond orbital stability, the radiation environment of a binary system presents challenges and complexities that single-star habitable zone calculations don't capture. In systems with two similar stars, a planet in a circumbinary orbit receives radiation from two sources simultaneously. But the total flux varies as the planet moves around the binary, and the two stars' positions relative to the planet change. The variation in received stellar flux is not as extreme as you might imagine for compact binaries where the two stars are always relatively close together from the planet's perspective. But it is real, and it drives seasonal cycles of a complexity that has no analog in our own solar system. For S-type planets orbiting one star in a binary, the situation is different. The planet orbits its primary star and receives relatively steady radiation from it, with the companion star contributing a varying background illumination as it moves through its own orbit. If the companion star is a red dwarf, cool, dim, and very different in color from the primary, the background illumination it contributes will be in a different spectral range than the primary's light, potentially affecting photosynthesis-like processes in a biosphere in ways that are difficult to predict. Consider Gamma Cephei, a binary star system about 45 light-years away in the constellation Cepheus. The primary star Gamma Cephei A is a subgiant slightly more massive and luminous than our Sun. Its companion, Gamma Cephei B, is a red dwarf orbiting at a distance of about 18 to 20 astronomical units. And orbiting Gamma Cephei A at a distance of about 2 astronomical units is a confirmed planet. Gamma Cephei AB, a giant planet detected through radial velocity measurements announced in 2002 after an initial detection in 1988 that was later retracted, then confirmed again with better data. This was one of the earliest confirmed planets in a binary star system. Gamma Cephei AB is too massive and too close to its star to be habitable itself. It's a giant planet likely similar to Jupiter, and its orbit at 2 astronomical units from a subgiant star would place it beyond the outer edge of the habitable zone. But the system demonstrates that giant planets, and therefore presumably smaller rocky planets that current instruments cannot yet detect, can form and persist in stable orbits around one star in a binary system with a companion at 20 astronomical units. The gravitational influence of Gamma Cephei b at that distance apparently did not prevent planet formation around the primary. This leads to a question that planetary scientists have worked hard to answer. Can planets form in binary systems in the first place? For a long time, the theoretical expectation was that binary companions would disrupt the protoplanetary disk around a young star, preventing the gentle accretion of dust into planetesimals and, eventually, planets. Tidal forces from the companion would stir up the disk, increase collision velocities between dust particles, and potentially drive the disk material away before it could coalesce into larger bodies. The observational evidence has complicated this picture considerably. Planets have now been found in binary systems of various separations, suggesting that planet formation is more robust than early theoretical models predicted. For wide binaries, companions at 50 astronomical units or more, the disk of the primary star appears largely unperturbed, and planet formation proceeds roughly as it would around a single star. For closer binaries, the situation is more complex but not uniformly hostile to planet formation. In some close binary systems, the circumbinary disk, a disk of material surrounding both stars, can form planets through a different accretion pathway than the standard one, taking advantage of the gravitational focusing and stirring provided by the binary pair rather than being disrupted by it. Alpha Centauri, our nearest stellar neighbors, was long considered a promising candidate for hosting rocky planets in the habitable zones of either Alpha Centauri A or B. At a binary separation of 11 to 36 astronomical units, the stable orbital zones around each individual star comfortably encompass the respective habitable zones. Radial velocity surveys have been conducted with increasing precision over the years, with mixed and sometimes controversial results. A claimed detection of a planet orbiting Alpha Centauri B, announced in 2012, was later retracted when the signal was determined to be instrumental noise rather than a planetary signature. As of current observational limits, no confirmed planet has been found around either star, but the absence of a detection is not evidence of absence. The instruments have not yet reached the sensitivity needed to definitively rule out small rocky planets in the habitable zones. The James Webb Space Telescope and future planned missions, including the Habitable Worlds Observatory concept, currently in early development, may eventually be capable of direct imaging spectroscopy of planets around Alpha Centauri, if they exist, allowing the direct detection of atmospheric biosignatures, oxygen, methane, water vapor, the chemical signatures of a living biosphere. That would be without qualification one of the most profound discoveries in the history of science. Now, let's return to that beach with two sunsets, because the question of what life on a binary world would actually experience is not just poetically interesting. It has scientific implications for how we think about the requirements for life and the contingency of our own evolutionary history. On a circumbinary planet orbiting a compact binary pair, say two stars of slightly different temperatures, orbiting each other in 10 days, the sky would present an experience of light and shadow with no earthly analog. During the period when one star passes in front of the other, from the planet's perspective, essentially a stellar eclipse from the ground, the total illumination would drop noticeably, though not to darkness. Shadows would behave strangely. The quality of the light would shift as the spectral balance between the two stars' contributions changed. If one star is warmer and bluer and the other cooler and redder, the light when both are visible simultaneously would be a blend neither the crisp neutral daylight of a single yellow star nor the ruddy diffuse light of a red dwarf, but something composite, something that no eye shaped by evolution on this world would have anticipated. Photosynthesis. The fundamental process by which most life on Earth captures energy from starlight is highly tuned to the specific spectral output of our sun. Plants on Earth absorb strongly in the red and blue portions of the visible spectrum and reflect green, which is why terrestrial vegetation appears green. On a world with two stars of different temperatures, the spectral mix available to photosynthetic organisms would be different. Life, if it evolved, there might well have developed pigments tuned to the specific blend of wavelengths available, producing vegetation of colors that no human eye has ever seen growing under skies lit by two different suns. One of the most striking ideas in astrobiology is that the color of vegetation on a planet can potentially be used as a biosignature, a remotely detectable signal of life. Earth's vegetation has a distinctive spectral feature called the red edge, a sharp increase in reflectivity at wavelengths just beyond the visible red, where chlorophyll stops absorbing, and the cell structure of leaves becomes highly reflective. In principle, this feature is detectable in the spectrum of light reflected from Earth's surface. On a world around a different star or two stars, the equivalent vegetation red edge might occur at different wavelengths, depending on which photons the dominant photosynthetic organisms had evolved to capture. Astrobiology around binary stars is a young field, but it is growing rapidly. The confirmation that circumbinary planets exist, that S-type planets in binary systems exist, and that at least some of these orbits fall within or near the habitable zones of their systems, has transformed the question from hypothetical to genuinely urgent. Given that roughly half of all Sun-like stars are in binary systems, the fraction of the galaxy's potentially habitable planets that orbit binary stars could be enormous. If we restrict our search for life to single-star systems by default, as early SETI and exoplanet programs tended to do, we may be systematically ignoring half or more of the universe's candidate worlds. Have you ever considered that the image we carry of a habitable world, a single warm sun, blue skies, one set of shadows at noon, might itself be a product of our particular circumstance rather than a universal requirement? That life, wherever it exists, adapts to the light it finds. The universe does not build worlds to match our expectations. It builds them according to its own preferences. And its preference, as we've established through this entire night's journey, is for company, for pairs, for the complex, layered, sometimes violent, sometimes gentle relationships between two stars sharing the same corner of space. The evidence suggests that worlds with two suns are not rare exceptions. They are likely common, perhaps extraordinarily common. And the life that might exist on them, if it exists, would look up at a sky that we cannot fully imagine adapted to light, that we have never seen, shaped by rhythms of day and season, and eclipse that have no name in any human language. And yet, in the most fundamental sense, that life would be doing exactly what life on Earth does, finding the light, using it, persisting, wondering perhaps, in whatever form wondering takes for it, whether it is alone in a universe that seems, the more carefully you look at it, to prefer things in pairs. As we let that thought settle softly into the quiet, the image of life adapting to a double sunrise of photosynthesis, tuned to composite starlight of shadows, pointing in two directions across an alien shore. There is one final thing to consider, one last thread to follow before this long night draws gently toward its close. Because everything we have explored, the dances, the mass transfers, the explosions, the gold, the possible worlds, all of it points toward a single quietly profound question. Not what binary stars do, or what they create, or what lies beneath them, but what they mean, what the fact of their existence, their prevalence, their deep interconnection tells us about the nature of the universe itself, and what it might, if we let it tell us about something closer to home. That is where the final chapter of tonight's journey takes us now. There is a question that sits at the end of every long journey through science, not a technical question, not a question about data or methodology or instrument sensitivity, but a quieter one, the kind that surfaces when the facts have been laid out, and the mechanisms explained and the examples given, and you find yourself sitting with all of it, letting it settle, and asking, what does this mean? Not what does it predict, or what does it imply for future research, or what further questions does it raise, but what does it mean in the oldest and most human sense of that word? We have traveled a long way tonight, from William Herschel grinding telescope mirrors by hand in 18th century England, to gravitational wave detectors registering ripples smaller than a proton in 2017. From John Goodrick, a deaf teenager in York, who correctly identified the nature of a demon star that had puzzled humanity for 3,000 years, to the Harvard computers whose patient hands mapped the spectral signatures of thousands of stars that the official record of science forgot to credit them for. From the invisible Berry center around which two stars waltz in perfect gravitational obedience to the kilonova that scattered gold across 100 million light-years of space and eventually into the ground beneath your feet. And underneath all of it, threaded through every discovery, every paradox, every explosion and merger and slow transfer of stolen mass, has been one persistent, quiet, almost gentle fact. The universe prefers pairs. Let's sit with that for a moment. Really sit with it. Because it is stranger and more significant than it first appears. Physics at its most fundamental level does not require binary stars to exist. The laws of gravity do not demand that stars form in pairs. A universe identical to ours in every physical law could in principle have produced stars that almost always formed alone, single independent, isolated, each burning through its fuel without reference to any companion. There is no conservation law that mandates companionship, no quantum number that requires partnership. And yet, when we survey the sky with the best instruments ever built, the Gaia space mission currently cataloging over 1 billion stars with sub-microarc second precision, we find that between 40 and 80% of stars, depending on mass, are gravitationally bound to at least one companion. The universe did not have to do this. It chose to, in the sense that its initial conditions and physical laws conspired to make it the overwhelmingly common outcome. There is something in that worth holding on to quietly as we come to the end of this night. The implications of binary star prevalence extend in every direction. We have touched on many of them: the chemical enrichment of the galaxy through novae and kilonovae, the precision distance measurements enabled by Type 1, a supernovae, the confirmation of general relativity through binary pulsar timing, the discovery of dark energy, the origin of heavy elements. But there is one implication we haven't yet addressed directly, one that connects the abstract astronomy of binary stars to the specific contingent story of how we came to exist here on this particular planet, orbiting this particular star. Our sun is by statistical measures somewhat unusual. It is a single star. It has no stellar companion. Given that 40 to 50% of sun-like stars are in binary systems, a single sun is not rare, but it is the minority case, not the majority. And this solitude may be deeply connected to the specific character of our solar system and the conditions that allowed complex life to develop here. Consider what a stellar companion would have done to our solar system. A companion star, at say 100 astronomical units, well within the range of typical binary separations, would gravitationally perturb the outer solar system over billions of years. The Oort cloud, the vast loosely bound halo of cometary nuclei that extends from roughly 2,000 to 100,000 astronomical units from the Sun, would be significantly destabilized by a companion at 100 astronomical units, sending greatly elevated numbers of comets into the inner solar system on collision courses with the planets. Earth in such a system might have experienced far more frequent and more severe impact events than the relatively quiet impact history of the last 500 million years that allowed complex life to flourish here. This does not mean life couldn't exist in binary systems. We've spent a considerable portion of tonight exploring the evidence that it could, but it does suggest that the specific configuration of life on Earth, its timing, its complexity, the particular evolutionary trajectory that led to intelligence may have been shaped in part by the absence of a solar companion. Our sun's solitude may be one of the many contingent factors that made us specifically us possible. There is a hypothesis somewhat controversial, never definitively confirmed, but periodically revived in the scientific literature that our sun once had a companion star. The hypothesis, sometimes called the Nemesis hypothesis, after the Greek goddess of retribution, was proposed in 1984 by physicists Richard Muller, Mark Davis, and Piet Hutt as a possible explanation for an apparent periodicity in the mass extinction record of Earth. Paleontological data suggested at the time that mass extinctions occurred roughly every 26 million years. Muller and his colleagues proposed that a distant dim companion star a red dwarf or brown dwarf on a highly elliptical orbit, taking 26 million years to complete periodically pass through the outer solar system, destabilizing the Oort cloud and sending a shower of comets toward the inner solar system, triggering mass extinctions through increased impact rates. The hypothesis was elegant, dramatic, and ultimately not confirmed. More careful analysis of the extinction record has not convincingly demonstrated the claimed periodicity in surveys of the sky have not found any candidate companion star. Most astronomers today consider the Nemesis hypothesis unlikely, but the fact that it was seriously proposed and seriously investigated, published in peer-reviewed journals by credible researchers, reflects how deeply the question of solar companionship penetrates the question of Earth's history and life's trajectory upon it. More recently, a different version of the solar companion hypothesis has gained some traction. Not Nemesis, but a much more distant and less catastrophic companion, possibly a wide binary, that separated from the Sun early in the solar system's history, when gravitational interactions with other young stars in the Sun's birth cluster disrupted the bond. Research suggests that most stars form in clusters, and that the Sun almost certainly formed in a cluster of hundreds to thousands of stars, roughly 4.5 billion years ago. In such a dense stellar environment, close gravitational encounters between young stars are common, and wide binary companions are frequently stolen or disrupted within the first 100 million years of a stellar system's life. It is entirely possible that the Sun once had a companion born in the same molecular cloud, sharing the same birth cluster that was pulled away in the gravitational chaos of the early solar neighborhood before the planets had even finished forming. If so, the Sun's current solitude is not a primordial condition, but an acquired one, a loss in the most cosmic sense of that word. Have you ever looked up at the night sky and felt without quite being able to articulate it that something vast and old was quietly present there? Something that remembered a time before us, before Earth, before the solar system itself. The stars remember, not in any conscious sense, but the record of what happened to them. Every mass transfer, every supernova, every merger, every disrupted binary orbit is written into their chemistry, their motion, their positions in the galaxy. The Milky Way is, among other things, an enormous archive of gravitational relationships. Who was bound to whom, for how long, what happened when the bond broke. Reading that archive is one of the deepest projects of modern astrophysics, and we are only at the beginning of it. The Gaia mission in this sense is not merely a positional survey, it is an archaeological excavation. By measuring the precise positions and velocities of over 1 billion stars, Gaia allows astronomers to trace stellar orbits backward in time to reconstruct at least approximately where stars were in the past, and which ones moved together, suggesting a shared origin in the same birth cluster. Pairs of stars that formed together but were later separated by gravitational interactions can sometimes be identified as co-moving pairs, stars that share similar velocities and compositions, even though they are now separated by many light years. Former companions still drifting through the galaxy in roughly parallel paths, like two old friends who move to different cities but still walk at the same pace. There is a term for these gravitationally separated former companions, wide co-moving pairs, and Gaia has found them in numbers that confirm the picture of a dynamic, chaotic early stellar environment where binary bonds were frequently formed and frequently broken, where the star you were born beside is not necessarily the star you will spend your life beside. The universe, it seems, is not sentimental about keeping its pairs together. It forms them readily and disrupts them freely according to the mathematics of gravitational dynamics and nothing else. And yet, some pairs endure. Some binary systems have maintained their gravitational bond for the full age of the galaxy for 12 or 13 billion years, through the formation of the disk, through multiple passages of spiral arms, through gravitational perturbations from countless passing stars and molecular clouds. Pairs that formed when the universe was less than 1 billion years old and are still together today, still orbiting their shared barycenter, still exchanging light and gravity, and in some cases, mass still dancing after all this time. The oldest known binary stars in the Milky Way belong to the galaxy's halo population, metal-poor stars formed in the earliest epochs of galactic history, before multiple generations of stellar evolution had enriched the interstellar medium with the heavier elements that later generations of stars contain. These ancient binaries are dim, cool, chemically simple, made mostly of hydrogen and helium, with traces of the lightest metals produced in the first few 100 million years after the Big Bang. They have been orbiting each other since a time so remote that trying to visualize it requires letting go of almost every familiar reference point. The Sun didn't exist. Earth didn't exist. The Milky Way was still assembling itself from smaller proto-galactic fragments. And these two stars were already circling each other, already locked in their gravitational waltz, already partners. 13 billion years, give or take. There is something about that time scale that does something quiet to the mind if you let it. Not the vertigo of incomprehensible size we've all felt, that looking at images of galaxy clusters or reading about the cosmic web. This is something different. This is the recognition that the universe's most intimate relationships, the ones defined not by scale, but by proximity, by the shared center of mass, by the slow, patient orbit of one around the other. Some of those relationships have been going on since almost the beginning of everything, and they are still going on right now tonight as you listen. Two stars circling each other in the dark for 13 billion years. No one watching for almost all of that time. No one to name them or measure them or wonder about them. Just the orbit, just the gravity, just the quiet, persistent fact of being bound together. If you've made it with us through this entire night, through Herschel and Goodrich, through spectral lines, and Roche lobes through Olgall's paradox, and GW170817 through the gold in your ring and the possible sunsets on worlds we cannot yet visit, then you have traveled further than you might realize, not just through astronomy, through the question of what it means for things to be connected, what it means for a relationship to endure, what it means for two things formed together to remain in orbit around a shared center that neither of them owns. The universe, as we've seen, is extraordinarily good at making pairs. It makes them in the chaos of collapsing molecular clouds, in the turbulence of stellar nurseries, in the gravitational dance of stars passing close enough to capture each other. It makes them at scales from stellar contact, two stars sharing one atmosphere, to separations of tens of thousands of astronomical units, where the bond is so gentle that it barely registers, but it persists. It makes them between ordinary stars and exotic remnants, white dwarfs, neutron stars, black holes pairing the old and the strange with the new and the ordinary, in combinations that produce some of the most energetic and chemically significant events in the cosmos. And then sometimes it separates them. Not out of indifference, but simply because the mathematics of gravity and the chaos of stellar environments don't preserve every bond. Some pairs survive for billions of years. Some are disrupted in millions. Some, like the hypothetical early companion of our Sun, may have been separated so long ago that we no longer have the observational evidence to confirm they ever existed. The universe forms connections and breaks them with equal facility, following no rule except the one that was present from the beginning. Mass, warps, space, guides, mass, and everything that has mass is in relationship with everything else, that has mass across every scale in every direction forever. What does this tell us at the end of a long night of watching the stars? Perhaps that isolation is not the natural state of things. That single stars like our Sun are the exception in a universe that defaults to companionship, that the gold in the most precious things we make, the calcium in our bones, the iron in our blood, all of it passed through violent binary relationships before it found its way to us. That the very tool we use to discover the accelerating expansion of the universe, the Type 1. A supernova is a product of one star, slowly accumulating the mass of another until the boundary was crossed and everything shattered. That the first direct detection of gravitational waves, humanity's newest sense, our ability to feel the geometry of space-time itself, was triggered by two neutron stars, former members of a binary system, completing a dance that had begun hundreds of millions of years before the first human looked up at the night sky. We are downstream from binary stars in more ways than we usually think to count. And perhaps if you'll allow one final thought to drift quietly into the space between science and something else, there is something worth carrying from tonight's long journey into the way you think about connection. Not as a metaphor mapped artificially onto astrophysics, but as a genuine observation about what the universe actually does, what it has always done, what it does right now in every molecular cloud and stellar nursery in every galaxy in the observable cosmos. The universe makes pairs. It invests them with the most fundamental force it possesses. It lets them shape each other, change each other, sometimes steal from each other, sometimes explode together in moments of extraordinary violence, sometimes drift together through billions of years of quiet orbital patience. And in doing so, it produces the chemical richness, the structural complexity, the layered beauty of a cosmos that was once just hydrogen and helium and dark and is now this. Stars that steal mass from their companions and scatter gold across space. A deaf teenager in York who correctly understood a demon star that had mystified humanity for 3,000 years. Women at Harvard who mapped the spectral fingerprints of 10,000 stars and received for decades little credit for it. Two neutron stars that spiraled together for 100 million years, and in their final second, confirmed the most important theory in modern physics and revealed the origin of the most precious metals on Earth. None of these stories is about a single thing standing alone. All of them are about what happens in the space between. Thank you genuinely deeply for spending this night here, for letting curiosity do the listening, as we said at the very beginning, for drifting through all of this with us from the ancient light of misunderstood double stars all the way to the gold atoms in the ground beneath your feet, and the gravitational waves passing through your body, right now, at this very moment, carrying news of some distant cosmic event you will never know the name of. The universe is full of things like that. Events without witnesses, dances without audiences, orbits that have been running since before the Earth existed that will continue long after it is gone. But tonight for a little while, we watched. We listened, we let the science whisper instead of shout, and that quietly is enough. Sleep well, dream gently, and the next time you see a single bright star in the evening sky, pause just for a moment and consider the possibility that it is not alone. That somewhere just beyond what your eye can resolve, there is another light circling it, patient and gravitationally faithful in a dance that has never once stopped. Good night, friends. The next quiet story is already waiting for you, and it begins somewhere you might not expect.